There are galaxies that spin in place, galaxies that drift along leisurely currents in space, and then, there's Leo the First. A ghostly, nearly invisible smudge in the darkness, so faint it was overlooked for most of human history. But hiding behind that silence is a mystery of staggering proportions. Because Leo the First isn't just orbiting the Milky Way, it's racing away from it. Faster than most galaxies of its kind. So fast, in fact, that it might just escape the Milky Way's gravity entirely. But before we continue, subscribe to the channel and like the video. Imagine a satellite, dwarfed in comparison to its hosts, tucked into a small halo of stars, gathering such cosmic momentum that it begins to flee. Not just drift away gently, but break free from a gravitational prison that spans hundreds of thousands of light years. This is not the story of a calm, obedient companion. This is the story of a renegade. A galactic fugitive. A galaxy on the run. We often think of the Milky Way as a kind of gravitational monarch, reigning over a swarm of satellite galaxies, small, dim systems that circle it in perpetuity, caught in its gravity well, their destinies entangled with ours. But Leo the First is threatening to change that narrative. If what we're seeing is correct, then Leo the First is slipping the chains of that dominion. And if it escapes, it will be among the first satellites ever observed doing so. That isn't just rare. It's unprecedented. What makes this event more astonishing is that Leo the First is not some flashy, flamboyant galaxy teeming with stars and gas and drama. It's quiet. Nearly invisible without long exposure imaging. There are more vivid galaxies. There are brighter ones. There are more chaotic ones. But few have captured astronomers' imaginations in quite the same way. Because while Leo the First doesn't scream for attention, it's performing a cosmic feat we can barely comprehend. Why is it moving so fast? What force launched it into this sprint? Is it a fluke of cosmic geometry? A result of gravitational violence? Or is there something more mysterious driving its speed, perhaps an echo of some ancient interaction, or a hidden property of the Milky Way's gravitational halo we've yet to understand? In the vastness of space, motion is everything. And when something moves too fast for gravity to keep it tethered, it ceases to be a prisoner of its system. Leo the First may be doing just that, pushing past the invisible frontier of the Milky Way's gravitational influence. That makes it a natural laboratory for astronomers. A chance to refine what we know, or thought we knew, about mass, motion, and the way galaxies hold on to their children. As we venture into the story of Leo the First, keep one thing in mind: this isn't just the tale of a small, dim satellite. It's the unfolding drama of escape, of momentum overpowering gravitational fate. A galaxy unbinding itself from the colossal grip of a spiral giant. And as we peel back the layers, from its faint discovery to the cosmic forces behind its speed, we begin to glimpse a new chapter in our understanding of galactic dynamics. Leo the First isn't just another data point. It's a revelation. Leo the First is what astronomers call a dwarf spheroidal galaxy. A quiet, dim, and ancient collection of stars, shaped more like a hazy ellipsoid than the grand spirals we're used to imagining when we think of galaxies. It lacks the swirling arms of the Milky Way, has no dense clusters of newborn stars, and contains very little gas or dust. It's not the kind of galaxy that stands out in a deep space photograph, nor is it bursting with colorful nebulae or dazzling stellar nurseries. In many ways, it seems like a ghost of a galaxy, silent, skeletal, and subtle. But its modest appearance belies an extraordinary importance. Located approximately 820,000 light-years from Earth, Leo the First floats on the edge of the Milky Way's domain. It lies in the constellation Leo, thus its name, and is one of the Milky Way's outermost satellite galaxies. In fact, among the known dwarf spheroidals that orbit our galaxy, Leo the First is among the most distant. And that distance isn't just a geographical detail, it's a clue, a fragment of a much larger puzzle about where Leo the First came from, where it's headed, and whether it truly belongs to the Milky Way at all. Despite being one of over 50 known satellite galaxies orbiting the Milky Way, Leo the First has carved out a unique reputation for itself. Most dwarf spheroidals cluster closer to the galactic center, forming a kind of faint, ragged halo of satellites. Leo I, on the other hand, is precariously far-flung. Its position at the outer rim of the galaxy's gravitational boundary raises fundamental questions. Is it still gravitationally bound to the Milky Way, or is it teetering on the brink of intergalactic freedom? This borderline existence makes Leo I invaluable to astronomers. It sits at the threshold between being a satellite and becoming an interloper, and that threshold is where some of the most revealing physics plays out. By studying galaxies like Leo I, especially those dancing near the edge of escape, scientists can better understand the shape and size of the Milky Way's dark matter halo, which acts as the galaxy's unseen gravitational skeleton. The further out a satellite galaxy lies, the more it tests the limits of the Milky Way's reach, helping to map out the invisible boundary where the galaxy's gravitational influence begins to fade into the cosmic background. And Leo I is not just important because of where it is, but because of what it is. As a dwarf spheroidal, it offers a window into the early epochs of galactic formation. These kinds of galaxies are thought to be among the universe's earliest building blocks, small systems that later merged and coalesced into larger galaxies. They contain mostly old stars, some dating back over 10 billion years, giving astronomers a stellar fossil record to study. By examining their compositions, we learn how galaxies like the Milky Way assembled over cosmic time. Yet Leo I stands out even among its dwarf companions. Its motion, its remoteness, its speed, none of it fits neatly within the box we typically use to categorize satellite galaxies. While most dwarf spheroidals have settled into predictable, slow, elliptical orbits, Leo I seems to have taken on a more extreme trajectory. Its path through space, when traced backward, doesn't suggest a long, leisurely orbit around the Milky Way. It looks more like a bullet, like something that may have only recently entered our galactic neighborhood, or something that's already on its way out. In essence, Leo I is a contradiction. It is both small and significant, faint and powerful, ancient and dynamic. A galaxy of few stars and little gas, yet one whose existence forces us to confront the most fundamental questions about how galaxies form, interact, and hold together across billions of years. It may not shine brightly in the night sky, but its presence is anything but dim in the eyes of astronomers. The story of Leo I begins, at least from our perspective here on Earth, in the middle of the 20th century, a time when astronomy was undergoing a quiet revolution. Telescopes were growing more powerful, photographic techniques were improving, and for the first time, astronomers were beginning to peer deep enough into the sky to detect the faintest companions of the Milky Way. But Leo I, even in this golden age of discovery, did not come easily. It was in 1950 that American astronomers Albert George Wilson and Robert George Harrington first identified Leo I. The discovery wasn't the result of some dramatic observation through a giant observatory lens. It came from painstaking analysis of photographic plates taken with the 48-inch Schmidt telescope at Palomar Observatory in California. At that time, astronomers were still cataloging nearby stars and searching for faint, fuzzy smudges that didn't behave like typical foreground stars. Leo I appeared as just such a smudge, so dim and diffuse that it was nearly indistinguishable from background noise. Initially, Leo I was barely more than an anomaly, an odd concentration of stars in a part of the sky where they didn't quite belong. But upon closer inspection, astronomers began to notice patterns. The object's light distribution wasn't random, it had a smooth, spheroidal shape. And the stars within it weren't scattered evenly like those in open clusters. They were ancient, red, and dim. This wasn't a random grouping, it was a coherent stellar system. A galaxy, albeit a small and unusually faint one. What made Leo I particularly tricky to spot was its proximity, at least visually, to Regulus, the brightest star in the constellation Leo. Regulus is a blue-white supergiant, and its intense glare and telescopic views made it difficult to spot anything faint in its immediate neighborhood. Leo I sits just about 12 arc-minutes north of Regulus, which means its feeble light is almost completely drowned out by the nearby star's brilliance in most observations. Detecting Leo I required long exposure photographic plates and extremely careful processing to tease out its subtle signature from the overwhelming brightness of Regulus. In fact, this proximity to such a prominent star may have delayed its discovery by decades. After its identification, follow-up studies were conducted to better understand what this ghostly object was. It was confirmed as a dwarf spheroidal galaxy through spectroscopic analysis, which helped reveal the velocities of the stars inside it. These velocity measurements showed that Leo I's stars were not part of the Milky Way's halo or foreground population. They were a distinct, gravitationally bound system. Further distance estimates, made using standard candles like RR Lyrae variables and red giant branch stars, placed Leo I just under 1 million light-years from Earth, firmly within the Milky Way's gravitational influence, but far enough out to be unusual. At the time of its discovery, Leo I became one of the most distant known satellites of the Milky Way, and one of the faintest. Its detection expanded the boundaries of what astronomers considered possible for galactic companions. Up to that point, most satellite galaxies had been found relatively nearby: Sagittarius, Fornax, Sculptor, all closer and easier to detect. Leo I demonstrated that the Milky Way's reach might be much farther and more populated than previously assumed, and that there could be entire galaxies lurking just beyond the threshold of visibility, hidden in plain sight. The discovery of Leo I also triggered a broader wave of searches for similar objects. If one such dim galaxy had eluded detection until 1950, how many others might be lurking out there, lost in the glow of brighter stars, or simply too faint to see with existing instruments? This line of questioning would eventually lead to the discovery of Leo II, its neighboring dwarf, and many other satellites that now form a growing census of the Milky Way's extended family. In hindsight, Leo I's discovery might seem quiet, no fanfare, no flash in the sky, but it marked a turning point in galactic astronomy. It reminded scientists that not all galaxies announce themselves loudly. Some whisper, hidden in the glare, waiting for the right observer with the right tools to find them. And when they are found, they often tell stories far more dramatic than their faintness suggests. From our vantage point on Earth, Leo I resides in a familiar celestial neighborhood, tucked within the boundaries of the constellation Leo, the Lion, one of the more recognizable star patterns in the night sky. This positioning gives Leo I its name, and also places it within a region of space that has fascinated astronomers and skywatchers for centuries. Leo is a bold and bright constellation, part of the zodiac, and its most prominent star, Regulus, is a cornerstone of its iconic shape. But it's precisely this brilliance that makes observing Leo I so difficult. Leo I lies just about 12 arcminutes to the north of Regulus, an incredibly close angular distance in astronomical terms. For comparison, the full moon spans about 30 arcminutes across the sky, so Leo I and Regulus are only about a third of a moon-width apart. Regulus, a massive blue-white star located about 79 light-years from Earth, dominates its region of the sky with intense brightness. Its glow is so strong that it easily overwhelms nearby objects, especially faint ones like Leo I. In observational astronomy, this is a significant complication. Even with modern imaging technology, the light from Regulus creates diffraction spikes, lens flares, and sensor noise that can mask faint galaxies like Leo I almost entirely. Because of this blinding proximity, Leo I isn't visible to the naked eye, not even through amateur telescopes. It requires a telescope with significant light-gathering power, a very dark sky, and precise coordinates to locate. Astronomers must carefully time their observations, often during optimal seasonal windows when Leo is high in the sky and atmospheric distortion is minimal. The best months for observing the constellation Leo, and by extension, Leo I, are February through April, when it reaches its highest point in the night sky for observers in the northern hemisphere. But even during these prime viewing times, Leo I is elusive. It has an extremely low surface brightness, meaning its light is spread out thinly across the sky rather than concentrated in a bright core. This makes it appear more like a soft, ghostly smudge than a sharply defined object. In fact, many amateur astronomers who point their telescopes toward Regulus might never realize they're looking right past an entire galaxy, albeit a tiny one in galactic terms. Without deep imaging, Leo I simply blends into the stellar background. To study Leo I in any meaningful detail, astronomers rely on long-exposure imaging, often using charge-coupled devices, CCDs, attached to large ground-based telescopes. These CCDs accumulate light over time, gradually building up enough signal to reveal the galaxy's faint glow. In some cases, astronomers will stack multiple images taken over different nights to enhance the visibility of Leo I and suppress background noise. This process allows them to extract the galaxy's profile from the light pollution and star glare around it, revealing its shape, size, and stellar population. Modern surveys, such as the Sloan Digital Sky Survey (SDSS), and deeper imaging efforts with the Subaru Telescope (VLT), Very Large Telescope, and Hubble Space Telescope, have dramatically improved our ability to analyze Leo I. These tools allow researchers to resolve individual stars within the galaxy, particularly red giants and horizontal branch stars, which serve as markers for distance and age. With the help of space-based instruments that operate above Earth's turbulent atmosphere, astronomers can bypass the atmospheric distortion that makes ground-based observations challenging. These space telescopes have been especially valuable in studying the outer halo of Leo I, where its stars become even more sparsely distributed. Another observational breakthrough came with spectroscopic surveys, which analyzed the light from Leo I's stars to determine their velocities and compositions. These surveys, such as those conducted with the Keck Observatory in Hawaii, allow astronomers to distinguish Leo I's stars from foreground Milky Way stars based on their motion and metallicity. Stars in Leo I tend to move in ways that are inconsistent with Milky Way stars in the same line of sight, and they show chemical signatures that are distinct, often with much lower metallicities, suggesting they are older and formed in a different environment. Leo I spans an angular diameter of about 12 arc-minutes across the sky, which corresponds to roughly 2,000 light-years in physical diameter, given its distance from us. That makes it small, far smaller than the Milky Way, which spans over 100,000 light-years, but still immense by human standards. If Leo I were brighter, it would be a striking feature in the sky, but its faintness renders it practically invisible unless targeted specifically. Its position relative to Regulus also offers an unusual observational challenge. Any study of Leo I must contend with optical contamination from scattered light, diffraction effects, and even reflections within telescope optics. This has prompted many observing teams to develop customized filters, image subtraction techniques, and even software pipelines designed specifically to extract Leo I's faint signal from the noisy environment around Regulus. There's an almost poetic irony in this. Leo I, one of the most dynamically intriguing satellites of the Milky Way, hides in the glare of a well-known, easy-to-find star. It's as though the galaxy is camouflaged, concealed in brilliance, revealing itself only to those who know precisely where, and how, to look. The difficulty of observing Leo I mirrors its status as an astrophysical anomaly, easy to overlook, but profoundly important once discovered. From Earth, Leo I may not offer the immediate visual drama of something like the Andromeda Galaxy or the Magellanic Clouds. But it has become a magnet for astronomers not because of how it looks, but because of what it means. Its location in the constellation Leo serves as a gateway, not just in terms of coordinates, but in terms of cosmological curiosity. It reminds us that some of the most extraordinary objects in the universe aren't always the ones that shine the brightest, but the ones that whisper secrets from the edges of visibility. In the grand arena of galactic satellites, Leo I is a phantom. You can't see it with the naked eye. You can't find it with a backyard telescope. But with the right tools, with deep enough imaging and careful analysis, it emerges, a delicate blur with a trajectory that might redefine how we think about galactic companionship. It's there, just barely. Silent, but screaming through space. In the traditional sense, a satellite galaxy is expected to orbit its host in a relatively stable, gravitationally bound loop, sometimes elongated, sometimes circular, but ultimately governed by the host's gravity. These are galaxies caught in a kind of cosmic partnership, drawn in by mutual history, held close by the immense gravity of a galactic titan like the Milky Way. But Leo I may not be one of them for much longer. Its story diverges from the norm, its movement hinting at something far more dramatic. Because unlike most satellite galaxies that slowly circle their hosts, Leo I is tearing through space at such a blistering pace that it may soon break free, or may already have. For decades, Leo I was assumed to be just another member of the Milky Way's extended satellite family, albeit a particularly distant and dim one. It fit the criteria. It was close enough to be considered gravitationally tied to the galaxy, and its location placed it well within the broad halo of dark matter and stars surrounding the Milky Way. But new data began to challenge that view. As instruments grew more precise and telescopes more powerful, astronomers began to scrutinize Leo I's motion with greater detail. What they found was shocking. Leo I was moving at a velocity that seemed inconsistent with a stable satellite orbit. Unlike more comfortably nestled companions like the fornax or sculptor dwarfs, Leo I isn't drifting leisurely. It's moving at nearly 200 kilometers per second relative to the Milky Way. To put that into perspective, that's fast enough to traverse the distance between the Earth and the Moon in less than half an hour. In galactic terms, this is a breakneck speed, fast enough that it may be unbound, meaning the gravitational tether connecting it to the Milky Way may have already snapped, or is hanging on by the faintest of threads. This velocity challenges the very definition of Leo I as a satellite. If a galaxy is no longer gravitationally bound, can we still call it a satellite? Or is it something else entirely, an interloper? A rogue? Perhaps even a visitor passing through our cosmic neighborhood on a one-time trajectory, never to return? The first serious reconsideration of Leo I's status came with deeper velocity measurements, especially those from Gaia, the European Space Agency's astrometric satellite. Gaia has revolutionized our understanding of stellar motion in the Milky Way and beyond, allowing astronomers to track individual stars with unprecedented precision. When researchers applied Gaia's data to Leo I, they found that not only was the galaxy moving fast, it was moving on a trajectory that didn't fit the tidy, closed-loop paths expected from bound satellites. Instead, Leo I appears to be following a radial orbit, a nearly straight-line path that plunges in toward the Milky Way's center and then slingshots outward. This type of motion is not typical for long-term companions, which usually exhibit more elliptical or circular orbits due to the stabilizing effects of gravitational interactions over billions of years. Radial orbits suggest something more violent, more temporary. Something entering or leaving. What's especially intriguing is the possibility that Leo I may have already made one close pass near the Milky Way's core, perhaps a few billion years ago. If that's true, it would explain much about its current speed. It could have gained momentum from a gravitational slingshot, much like spacecraft do when using planets to accelerate toward distant targets. But in this case, the spacecraft is a galaxy, and the planet is the colossal mass of the Milky Way. If Leo I came too close, too fast, it could have been catapulted outward, converting its potential energy into a wild burst of motion, now carrying it to the edge of the Milky Way's influence, and possibly beyond. This presents a profound conceptual shift. Leo I may not be a satellite in the traditional sense. It might be a former satellite, a galaxy that has interacted with the Milky Way once, perhaps in a dramatic close encounter, and is now fleeing. Or it might be something even more exotic, a flyby galaxy, not originally bound to the Milky Way at all, merely passing through the local group in a cosmic near-miss. These kinds of events are exceedingly rare, but they're not impossible. In a universe governed by chaos and gravity, collisions and close calls are inevitable given enough time. If Leo I is indeed on an escape trajectory, it could become one of the first galaxies we've ever observed actively leaving the gravitational grip of the Milky Way. That would make it a singular case, an object that teaches us about the edge conditions of galactic binding. Just how massive is the Milky Way? Just how far does its dark matter halo extend? And what happens to a galaxy as it leaves the shelter of a larger system and heads into the intergalactic void? Such questions are no longer theoretical. They're real, tangible, and tied to Leo I's peculiar motion. It doesn't behave like a loyal companion. It doesn't stay within the safe confines of a stable orbit. It bolts. And that flight, that outward momentum, is what makes Leo the First so fascinating, and so difficult to classify. In the grand scheme of galactic taxonomy, we may need a new category for objects like Leo the First, galaxies that look like satellites from a distance, but are actually in transition, crossing the invisible threshold between gravitational subjugation and freedom. Leo the First may not be a prisoner of the Milky Way. It may be a fugitive, caught in the act of escape. Measuring the speed of a galaxy like Leo the First is no easy task, especially when it's as faint and distant as this elusive dwarf spheroidal. But understanding how fast Leo the First is moving, and in what direction, is critical to answering one of the most pressing questions in modern galactic astronomy. Is Leo the First still bound to the Milky Way, or is it escaping into the dark intergalactic void? The process of determining Leo I's velocity relative to the Milky Way has evolved significantly over the decades, beginning with rough estimates, and now refined to high precision thanks to an extraordinary confluence of advanced instruments, long-term data collection, and space-based observatories like the European Space Agency's Gaia satellite. To measure how fast Leo the First is moving, astronomers break its motion into two components: radial velocity, the speed at which it is moving toward or away from us, and tangential velocity, the speed at which it moves across the sky, perpendicular to our line of sight. Both are critical, but they're measured in very different ways, and the tangential component is especially difficult to detect in such a remote and faint galaxy. The radial velocity is measured using the Doppler effect, the same principle that makes an ambulance siren shift in pitch as it drives past. When Leo I's stars move toward us, their light is slightly compressed, shifting toward the blue end of the spectrum. When they move away, the light is stretched and redshifted. By carefully measuring the spectral lines of individual stars within Leo the First and comparing them to known laboratory values, astronomers can determine how fast those stars are receding from us. In Leo I's case, this component was the first to be determined, as early as the 1990s, thanks to sensitive spectrographs mounted on ground-based telescopes like the Keck Observatory in Hawaii and the Very Large Telescope, VLT, in Chile. What those measurements showed was striking. Leo the First has a radial velocity of around plus 285 km/s, meaning it's moving away from us very quickly. But radial velocity alone doesn't give us the full picture. A galaxy could be moving away from us while still orbiting the Milky Way in a large elliptical loop. To know whether Leo the First is really on an escape trajectory, we also need to know how fast it's moving across the sky, its proper motion, and that's where the challenges truly begin. Because Leo the First is about 820,000 light-years away, its motion across the sky is incredibly small from our point of view. Even if it were moving at hundreds of kilometers per second, the shift in its position would be tiny, measured in microarcseconds per year, a level of detail that's completely beyond the reach of most ground-based instruments. For decades, this component remained a mystery. But that changed with the launch of Gaia, a satellite designed to chart the positions and motions of over 1 billion stars in our galaxy with extraordinary accuracy. Gaia doesn't just track stars in the Milky Way, it also tracks stars in satellite galaxies like Leo the First. By monitoring the tiny shifts in the positions of Leo I's brightest stars over the course of several years, Gaia has been able to calculate their proper motion. These measurements are so precise that they can detect changes smaller than the width of a human hair seen from 1,000 kilometers away. With this data, astronomers were finally able to compute Leo I's three-dimensional velocity vector, a full accounting of how fast and in what direction it's moving through space relative to the Milky Way's center. The results were jaw-dropping. The combined radial and tangential components give Leo the First a total velocity of around 196 km per second relative to the Milky Way, with some estimates pushing that value slightly higher depending on the assumed mass and gravitational potential of the Milky Way itself. This velocity is not just high, it's exceptional. It places Leo the First among the fastest-moving satellite galaxies known in the local group. And more importantly, When this speed is compared to the escape velocity at Leo I's distance from the galactic center, it begins to look like Leo I may be moving too fast to remain gravitationally bound. To determine that, astronomers also have to model the gravitational potential of the Milky Way, especially the distribution of its dark matter halo, which dominates the galaxy's mass at large distances. By plugging in various models for the Milky Way's mass profile, they can calculate the escape velocity at Leo I's position, essentially, the speed an object must reach to break free of the galaxy's gravitational pull from that distance. Many models place the escape velocity at Leo I's distance between 180 and 200 km per second, depending on assumptions about the Milky Way's total mass, which is still under debate. That means Leo I is either right on the edge of escape, or has already exceeded it, making its status as a satellite questionable at best. What's fascinating is how this single velocity number, just under 200 km per second, carries such enormous implications. If Leo I is just under the escape threshold, it could still be a bound satellite, perhaps on a very long, elliptical orbit that will eventually pull it back. But if it's over the limit, even by a small margin, then it's already on a hyperbolic trajectory, destined to drift away from the Milky Way forever. That's the razor's edge that Leo I walks. The uncertainty stems in part from the uncertainties in the Milky Way's mass. If the galaxy is more massive than we think, then its escape velocity is higher, and Leo I might still be bound. But if the Milky Way is on the lighter end of estimates, then Leo I is already gone, moving beyond the limits of its gravitational leash. This realization has transformed Leo I from a faint, barely noticed satellite into a crucial probe of galactic dynamics. It's not just about measuring the speed of a galaxy, it's about testing the limits of gravity, redefining what we consider a galactic boundary, and gaining insight into the dark matter structure of our own home galaxy. And all of this has only been possible thanks to the convergence of technologies that would have been unthinkable a few decades ago. Without Gaia's precision astrometry, without deep spectroscopic surveys from the world's largest telescopes, Leo I's motion would remain a blur of uncertainty. But today, we can track its path with such accuracy that we can see it straining against the grip of the Milky Way, like a stone hurled through the heavens, just fast enough to leave behind the gravitational empire it once served. When we say Leo I might be too fast for gravity, we're not speaking metaphorically. We're confronting one of the most fundamental concepts in physics, escape velocity, the speed at which an object must travel to completely overcome the gravitational pull of a massive body. It's the cosmic speed limit for departure. Exceed it, and you're free. Fall short, and you're destined to return. For Earth, the escape velocity is about 11.2 km per second. That's how fast a spacecraft has to travel to leave Earth's gravitational influence without further propulsion. But scale that up to galactic proportions and things get dramatically more complicated. The Milky Way isn't just one object, it's an enormous, diffuse system, composed of billions of stars, gas clouds, and critically a dark matter halo that extends far beyond the visible edge of the galaxy. This invisible halo accounts for the bulk of the Milky Way's mass, and it's what determines the strength and reach of our galaxy's gravitational pull. At the distance of Leo I, roughly 820,000 light-years from the galactic center, the gravitational field is weaker than it is closer in, but it's still significant. If you imagine the Milky Way's gravity as a deep bowl, the stars in the inner disk are rolling tightly near the bottom. Leo I is way out near the rim. That means the velocity required to escape is lower than it would be closer in, but it's still not trivial. Based on current models of the Milky Way's mass, the escape velocity at Leo I's distance is somewhere between 170 and 200 km per second. That range exists because of ongoing uncertainty about the total mass of the Milky Way and how its dark matter is distributed. So what happens if Leo I is moving faster than that escape velocity? It means it has enough energy, kinetic energy from its motion, to never fall back. Just like a spacecraft that escapes Earth's gravity, Leo I would continue on its outward journey, slowing gradually as it climbs out of the Milky Way's gravitational well, but never stopping, and never turning back. It would drift into intergalactic space, a region so vast and empty that the nearest major gravitational source might be millions of light-years away. In other words, Leo I would become a rogue galaxy, unbound and independent, no longer a satellite of any major system. This raises profound questions, both observational and theoretical. First, from an observational standpoint, is Leo I already escaping, or is it just barely clinging to the edge of the Milky Way's influence? That depends on two crucial variables: the total mass of the Milky Way, and the precise velocity vector of Leo I. The better we can measure those values, the more confidently we can answer the question. The challenge is that the Milky Way's mass is not something we can measure directly. We have to infer it from the motion of stars and satellite galaxies, objects like Leo I. In a strange twist, the very act of asking whether Leo I is escaping requires us to assume a value for the Milky Way's mass, but that same assumption is shaped by Leo I's motion. It's a kind of feedback loop. Our model of the galaxy's mass affects how we interpret Leo I's speed, and Leo I's speed, in turn, affects how we estimate the galaxy's mass. Then there's the theoretical dimension. Galaxies like Leo I are typically assumed to be gravitationally bound to larger hosts. That's how structure forms in the universe. Small systems get drawn into larger ones, forming cosmic hierarchies. But what if some small galaxies never get captured at all? Or what if they were captured and then ejected, flung out through gravitational interactions with the host or other satellites? This would suggest that the Milky Way's halo isn't a static collection of satellites, but a dynamic, evolving structure, constantly changing as galaxies come and go. One theory suggests that Leo I may have made a single close pass by the Milky Way in the past, possibly a few billion years ago, and that during this encounter, it experienced a kind of gravitational slingshot. If it passed close enough to the dense inner regions of the Milky Way, its velocity could have been dramatically increased, similar to how we use planetary flybys to accelerate spacecraft in interplanetary missions. In this scenario, Leo I was bound once, but it may no longer be. That would make it a transient satellite, not a permanent member of the Milky Way's retinue. Alternatively, Leo I might never have been bound at all. It could be a flyby galaxy, an object formed independently in the local group and now simply passing close to the Milky Way by cosmic coincidence. This is a far more radical idea, because it challenges our entire framework for understanding how dwarf galaxies interact with larger systems. But it's not impossible. In the vast timescales and volumes of the cosmos, close passes and near captures do happen. Gravity is a game of momentum and timing. If Leo I is indeed too fast for gravity, if its velocity exceeds the escape speed of the Milky Way, then it's doing something exceptionally rare. It would be one of the only known galactic satellites in the process of escaping a major galaxy. This is not a trivial footnote. It would be a cosmic milestone, reshaping how we think about the boundaries of galaxies, the permanence of satellite systems, and the subtle gravitational dances that occur in the outskirts of galactic halos. And yet, Leo I doesn't look like a galaxy in a hurry. It's faint. It's diffuse. Its stars are mostly old. There's no sign of violent disruption or intense star formation. It's serene, almost indifferent. But beneath that calm facade, it's moving with incredible purpose, almost 200 kilometers per second, away from the Milky Way, toward an uncertain fate. So when we ask, how fast is too fast? The answer, in Leo I's case, may be this fast. Fast enough to defy the gravitational grip of a trillion solar mass galaxy. Fast enough to rewrite the story of what it means to be a satellite. Fast enough to turn a faint, nearly invisible smudge in the sky into a case study in cosmic liberation. Gravity, in its quiet persistence, is the architect of the cosmos. It shapes galaxies, sculpts stars, binds moons to planets and planets to stars. But even gravity has its limits. For any massive object, there exists a point beyond which its gravitational pull can no longer hold on to something moving too quickly. That critical threshold is known as escape velocity, a defining line between captivity and freedom. For the Milky Way, this limit is vast, complex, and in the case of Leo I, potentially already broken. To understand escape velocity in galactic terms, imagine a ball being thrown upward on Earth. If it's tossed gently, it falls back quickly. Throw it harder, and it goes higher, but eventually returns. Only at a certain launch speed, around 11.2 kilometers per second, will the ball escape Earth's pull entirely. This is escape velocity, and the same principle applies to galaxies. The deeper you are in a gravitational well, the faster you must go to break free. In galaxies, this gravitational well is created not just by visible matter, stars, gas, dust, but overwhelmingly by dark matter, an invisible halo of mass surrounding the galaxy. The Milky Way's escape velocity is not a single number. It changes with distance. Near the galactic center, where stars are densely packed and the gravitational field is intense, escape velocity is highest, upward of 600 kilometers per second. But as you move outward, past the bright central bulge, beyond the spiral arms, into the sparse and ghostly halo where dark matter dominates, that number decreases. At the solar neighborhood, about 26,000 light-years from the center, the escape velocity is roughly 525 kilometers per second. But at Leo I's position, 820,000 light-years away, nearly 32 times farther, it is much lower. Here's where things get nuanced. Depending on the total mass of the Milky Way, and how far its dark matter halo extends, escape velocity at Leo I's location could be as low as 170 kilometers per second or as high as 200 kilometers per second. This is a relatively narrow window, but it's the one that matters most. Leo I, based on the most recent measurements, is moving at around 196 kilometers per second relative to the center of the Milky Way. That's near the upper edge of the theoretical escape speed at that distance. If the Milky Way is on the more massive end of estimates, around 1.6 trillion solar masses, then its gravitational influence stretches farther, and the escape speed at Leo I's position is likely closer to 200 kilometers per second. In that case, Leo I might still be marginally bound, destined to slow down and return in a looping, highly elliptical orbit. But if the Milky Way is less massive, say 800 billion to 1 trillion solar masses, then its gravitational boundary is smaller, and Leo I's current speed would exceed escape velocity. In that scenario, it's no longer bound, it's on a hyperbolic trajectory, escaping forever. To determine which case is true, scientists rely on detailed modeling of the Milky Way's mass distribution. This is complicated by the fact that dark matter doesn't emit light or energy, it only interacts through gravity. So astronomers must infer its presence and extent by observing the motions of stars, gas clouds, and satellite galaxies. It's a bit like trying to weigh a city by watching how fast birds fly over it. The faster they move, the deeper the gravity well must be. Leo I plays a crucial role in this process. Because it lies so far out, its motion serves as a test particle, an extreme example that pushes the limits of the Milky Way's gravitational influence. If Leo I is escaping, it places a hard constraint on the galaxy's mass. It must be low enough for Leo I to fly free. If it isn't escaping, the galaxy must be more massive than previously thought. This makes Leo I not just an interesting object on its own, but a cosmic ruler, a way to measure the unmeasurable. Its speed doesn't just tell us about itself, it tells us about the galaxy it may be leaving behind. The closer it is to the escape threshold, the more valuable it becomes as a calibrator for the Milky Way's gravitational potential. There's also an important conceptual layer here. Galactic escape isn't a binary switch. In classical Newtonian physics, sure, it's a clear line. But in the real universe, things get fuzzier. If Leo I is moving just below escape velocity, it may still escape over time, pulled slightly by other galaxies, influenced by large-scale cosmic flows, or nudged by interactions with dark matter substructures. On the other hand, if it's just barely over the limit, gravitational drag, tidal forces, or even past encounters could slow it enough to pull it back in. The edge of a galaxy's gravity is not a wall, it's a gradient. This leads to another question: where exactly does the Milky Way end? If Leo I can potentially escape, Does that mean the Milky Way's edge is closer than we thought? Or does it mean our galaxy has tentacles of gravitational influence stretching far into space, touching objects we didn't realize were connected? One possible comparison is with cometary orbits around the Sun. Some comets travel in nearly parabolic or hyperbolic paths, barely bound, just dipping into the inner solar system before swinging back out for thousands of years, or never returning. Leo I may be behaving similarly, on a vast, million-year flyby, arcing in from the depths of the local group and now sailing away into intergalactic space. The possibility that we are witnessing this moment, this transition from bound to unbound, is extraordinary. In cosmic terms, these events are rare and fleeting. The vast majority of satellite galaxies stay bound to their hosts, pulled into tight orbits, gradually merging over billions of years. But Leo I may be on a different trajectory entirely, its fate sealed not by slow merger, but by sudden escape. It's important to stress that whether or not Leo I escapes depends as much on our understanding of gravity at large scales as it does on the galaxy's motion itself. Some alternative theories to dark matter, like modified Newtonian dynamics, propose changes to the laws of gravity at low accelerations, such as those experienced at the edge of galactic halos. If any of these ideas are correct, they could shift the threshold for escape, redefining Leo I's trajectory once again. But under the prevailing standard model of cosmology, with cold dark matter and general relativity governing the large-scale structure of the universe, Leo I is skating the razor's edge. Its velocity is high, its distance is vast, and its trajectory is unlike that of any comfortably orbiting satellite. Gravity's limit, for this little galaxy, may already be behind it. Leo I's blistering speed, nearly 200 kilometers per second relative to the Milky Way, isn't just an astronomical curiosity. It's a riddle, a symptom of deep and possibly violent history. Galaxies don't just accelerate on their own. Their motion is shaped by the gravitational currents of the universe, molded by ancient interactions, the architecture of dark matter, and perhaps even long-forgotten collisions. The big question is, what exactly gave Leo I this extraordinary momentum? One of the leading theories is that Leo I's velocity is the result of tidal interactions with the Milky Way itself. When a smaller galaxy passes close to a much larger one, tidal forces, differences in gravitational pull across the galaxy, can stretch, compress, and even fling objects outward. The closer the pass, the more intense the interaction. These tides aren't just passive forces. They're capable of reshaping a galaxy's structure and altering its motion forever. If Leo I once dipped deep into the Milky Way's gravitational center, especially in a close, radial orbit, it may have experienced such a tidal encounter. During that pass, stars could have been stripped away, its structure distorted, and, critically, its velocity altered. Simulations of satellite galaxies interacting with massive hosts often show that such encounters can pump kinetic energy into the smaller galaxy. Like a ball thrown into a gravitational slingshot, Leo I may have gained speed from its plunge through the dense inner halo. These slingshots aren't necessarily symmetrical. Depending on the angle and timing of the pass, the galaxy might not slow down again. Instead, it accelerates outward, heading for the gravitational frontier and potentially beyond. Another compelling piece of this puzzle lies in Leo I's possible history of collisions or close interactions with other dwarf galaxies. The Milky Way doesn't exist in isolation. It has dozens of satellite galaxies, many of which are on chaotic paths and have interacted with each other across billions of years. If Leo I had a past encounter with another dwarf, perhaps Leo II, or one of the now-dissolved ultra-faint galaxies that once populated the Milky Way's outskirts, it could have received a significant gravitational kick. Such an encounter doesn't need to be a direct collision. Even a close pass could have disrupted Leo I's original orbit, altering its momentum and setting it on a more radial trajectory. In this scenario, Leo I's current path might be the result of a chain reaction, first influenced by a neighboring dwarf, then by the tidal pull of the Milky Way, until its velocity was pushed to the extreme. This idea of group infall, multiple dwarf galaxies falling into the Milky Way together as a coherent structure, has gained traction in recent years. Some satellites, including Leo I and Leo II, appear to be moving along similar orbital paths, suggesting they may have entered the Milky Way system as part of a group. In such a scenario, gravitational interactions between group members can act as dynamical triggers. The gravitational tug-of-war between multiple galaxies can redistribute momentum, speeding up some members and slowing others. Leo I might be the winner of that exchange, thrown outward by its former companions. But the real wild card in this equation is dark matter. Leo I, like most dwarf spheroidal galaxies, is thought to be heavily dominated by dark matter, in fact, more so than ordinary stars or gas. Observations show that its stars move too quickly to be held together by visible matter alone. That suggests a massive dark matter halo enveloping the galaxy, possibly extending far beyond its faint stellar boundary. This invisible halo provides gravitational cohesion internally, but could it also affect Leo I's motion through space? Some researchers speculate that the shape and density of Leo I's dark matter halo could make it more resistant to tidal disruption, allowing it to pass through the Milky Way's halo relatively intact while retaining more of its velocity. Others propose that dark matter interactions with the Milky Way's halo, possibly involving tidal stripping or gravitational resonances, could add energy to Leo I's motion. There's even speculation about whether Leo I's current trajectory might hint at an asymmetric distribution of dark matter in the Milky Way itself. If our galaxy's halo isn't spherical, but more ellipsoidal or lopsided, certain infall trajectories, like Leo I's, could be funneled or accelerated in ways that defy simpler models. Still, even deeper questions linger. Could Leo I be the remnant of a once larger galaxy, heavily stripped by past interactions with the Milky Way? If so, then what remains is just a high-speed core, the shrunken survivor of a once more massive system. In this scenario, Leo I's current speed would be the final stage of a long, brutal history of stripping and slingshotting. It could be the scarred bullet of a galactic encounter that took place long before humans first looked up at the night sky. There's also the exotic but intriguing idea that Leo I was never a typical satellite at all. It may have formed independently, perhaps in a filament of dark matter on the outskirts of the local group, and is only now making its first, and last, close pass to the Milky Way. In this case, Leo I would be a flyby galaxy, a cosmic traveler caught in a brief interaction, gaining speed from the gravitational pull of the Milky Way but never truly captured by it. This idea, while dramatic, is supported by some cosmological simulations. Large-scale models of structure formation in the universe occasionally show small galaxies that don't become permanent satellites of larger hosts. Instead, they pass near a galaxy like the Milky Way, are deflected by its gravity, and continue on their path through the intergalactic medium. These flybys are rare, but not impossible, and Leo I may be the first real-world example we've detected. And let's not ignore the possibility that a combination of all these factors is at play. The universe rarely offers clean, simple causes. Leo I's velocity may result from a confluence of events: early formation in a dark matter-rich environment, followed by group infall, a slingshot through the Milky Way's core, and perhaps a gravitational kick from a neighboring dwarf galaxy. Over billions of years, each of these events could add a piece to the puzzle, building up Leo I's incredible speed like a snowball rolling downhill. Ultimately, Leo I is a living fossil of motion. Its speed is a storybook written in gravitational interactions, dark matter dynamics, and deep time. It may be fast, but it isn't careless. Every kilometer per second it carries is a whisper from some past encounter, some cosmic tug or twist that left its mark. And as it continues on its path, perhaps away from the Milky Way forever, it carries with it the sum of those moments, moving like a ghost fleeing the scene of an ancient, forgotten war. To truly understand Leo I's unusual velocity and structural integrity, we must confront a presence that dominates its mass but remains invisible: dark matter. Though it neither emits nor absorbs light, dark matter is believed to make up the bulk of Leo I's mass, possibly more than 99% of it. This invisible component is not just an afterthought in Leo I's story. It is central to the galaxy's identity, evolution, and extraordinary motion. Without it, Leo I would likely never have survived its encounters with the Milky Way, let alone maintained the speed it's now exhibiting. Dark matter in Leo I reveals itself not through direct observation, but through the motion of its stars. When astronomers look at Leo I, they see a small, faint collection of stars, perhaps a few million in total, spread across a spheroidal volume roughly 2,000 light-years across. The galaxy contains very little gas and is not forming new stars, making it structurally simple. Yet the stars it does contain move with surprising speed, especially for such a small and dim system. These stars aren't flying apart though, which suggests that something massive is holding them together. That something is dark matter. The gravitational pull needed to keep Leo I's stars bound within its boundaries cannot be accounted for by the stars alone. When astronomers calculate the total visible mass of Leo I, meaning its stars, they come up with only a tiny fraction of what's needed to keep the galaxy intact. But when they apply the virial theorem, a method of calculating a system's mass based on the average speeds of objects within it, the results indicate a mass of around 2 times 10 solar masses, far more than the combined mass of all its visible stars. This discrepancy is one of the strongest indicators of dark matter, and Leo I is a textbook example of this gravitational anomaly. This makes Leo I what astronomers call a dark matter-dominated dwarf spheroidal galaxy. It's among the most extreme examples in the local group, a tiny galaxy where dark matter completely outweighs its luminous component. In practical terms, that means its stars are like dust motes suspended in a nearly invisible but enormously massive fog. The fog, in this case, is its dark matter halo, believed to extend well beyond its visible edge, creating a gravitational cocoon that maintains the galaxy's cohesion. And this is where things get truly interesting. That same dark matter halo that keeps Leo I intact might also play a crucial role in its overall dynamics, including its survival through tidal forces, and its current high-velocity motion through space. Let's begin with tidal resilience. When a small galaxy passes near a much larger one, like the Milky Way, it is subjected to intense gravitational shearing, tides that can strip stars, stretch the system, or even tear it apart entirely. This fate has likely befallen several former dwarf galaxies in the local group, whose remnants now appear as streams or stellar clouds trailing through the Milky Way's halo. But Leo I has no such stream, at least not an obvious one. Despite likely making a close approach to the Milky Way, it remains largely intact. How? The leading explanation is that its dense dark matter halo has shielded it from destruction. A compact and massive dark matter core provides the binding energy to hold onto stars, even under extreme tidal stress. This idea is supported by simulations that show dwarf galaxies with concentrated dark matter halos are far more likely to survive galactic encounters intact. Leo I's structure today is indirect proof of that invisible fortress. But the influence of dark matter doesn't stop at protection. It may also be contributing to Leo I's ability to accelerate. In high-precision simulations of galaxy evolution, especially those that incorporate hydrodynamics and dark matter physics, satellite galaxies can gain speed through gravitational interactions not just with the visible matter in the Milky Way, but also with the dark matter substructures within the Milky Way's halo. These substructures, dense clumps or streams of dark matter left over from earlier accretion events, can exert small but cumulative gravitational forces that affect a satellite's orbit over time. If Leo I has passed near or through one of these dark matter subhalos, it could have received a gravitational nudge, subtly altering its trajectory. These nudges may not seem significant individually, but over billions of years, they could sum to a measurable change in speed. And since we can't see the subhalos directly, we have to infer their presence through phenomena like this: galaxies with unexpectedly high velocities or strange orbits. Moreover, Leo I's own dark matter content affects how it interacts with the Milky Way's dark halo. Instead of being a passive body falling through a fixed gravitational field, Leo I can actually induce changes in the dark matter distribution around it, creating a gravitational wake, or even a mutual response between its halo and that of the Milky Way. This dynamic interplay can further tweak its velocity, depending on the density contrast, the relative speed, and the geometry of the encounter. Another point worth exploring is the possibility that Leo I's dark matter halo has itself evolved. It might have been even more massive in the distant past, perhaps enveloping a significantly larger galaxy that was gradually stripped by the Milky Way's gravity over multiple passes. In this scenario, what we see now, Leo I as a small, dark matter-dominated core, is simply the remaining nugget of a more massive progenitor. That progenitor may have had a more substantial gravitational well, allowing it to gain speed more efficiently during interactions with other structures, including the Milky Way. If true, that would make Leo I a survivor of galactic cannibalism, the last fragment of a once larger galaxy. Its dark matter halo, though diminished, would still be sufficient to keep it together and influence its velocity, especially if it's now moving on a radial or near hyperbolic path. In essence, dark matter acts both as a shield and a slingshot for Leo I. It protects the galaxy from tidal destruction, while also subtly sculpting its motion through interactions both internal and external. Without its dark matter halo, Leo I would not be the fast-moving, coherent system we observe today. It might not exist at all. But with it, Leo I becomes a living example of dark matter's cosmic influence, a ghostly galaxy, wrapped in invisible mass, accelerating through the universe in defiance of ordinary gravitational expectations. What Leo I offers is more than a test of galactic escape, it's a probe into the architecture of dark matter itself. By studying how it moves, how it survives, and how it holds together, astronomers can reverse engineer the properties of its halo, and perhaps even glimpse the fundamental nature of the unseen majority of the universe. Because while Leo I may be faint, its message is loud and clear: dark matter matters. It is not only the glue that binds galaxies together, but also a hidden engine driving their most unexpected journeys. In the grand theater of the cosmos, where galaxies like Andromeda blaze with billions of stars and spiral arms stretching across hundreds of thousands of light years, Leo I appears almost invisible. It doesn't dazzle. It doesn't roar. Instead, it whispers. This is the realm of the ghost galaxies, faint, diffuse, and hauntingly quiet, and Leo I is one of their most enigmatic representatives. To the untrained eye, Leo I doesn't even look like a galaxy at all. Observed through a small telescope, it appears as a dim, formless patch of light, so faint that it eluded detection for millennia. It wasn't until the mid-20th century that it was even confirmed to exist, and even then, only through careful photographic surveys that could pick up its ghostly glow against the background of the constellation Leo. Leo I is a dwarf spheroidal galaxy, meaning it lacks the vibrant structure of spiral galaxies or the chaotic brilliance of irregular ones. It has no discernible arms, no bulging core, and no bright blue clusters of newborn stars. Instead, it is a diffuse, spherical cloud of mostly ancient stars, spread thin across a region roughly 2,000 light-years in diameter. The stars are so sparsely distributed that the galaxy appears almost transparent, like a cosmic wisp drifting silently on the edge of the Milky Way's gravitational influence. Its low luminosity is a defining feature. In terms of absolute magnitude, Leo I ranks among the faintest known galaxies in the local group. Estimates suggest that it contains only a few million stars, roughly 1,000th the number in the Milky Way. And yet, these stars are not young and bright. Most are ancient, red, and low in mass, long-lived remnants from an early era of star formation. This gives Leo I a reddish hue when examined in detail, indicative of a population dominated by old, metal-poor stars formed over 10 billion years ago. What's especially intriguing is how undetectable Leo I is in casual observations. Its surface brightness, the amount of light it emits per unit area, is staggeringly low. This is why it remained hidden for so long despite being relatively close in galactic terms. It's not the distance that made it hard to find, it's the fact that its stars are so thinly spread and its light so faint that it gets drowned out by the sky's natural brightness and foreground stars in the Milky Way. It's for this reason that astronomers often refer to Leo I and galaxies like it as ghost galaxies. They exist in the dark spaces between brighter systems, nearly invisible to traditional surveys. They float through the galactic halo, detached and dim, like fossil embers from a time long gone. Their low brightness also means they are incredibly difficult to study in detail. Only with large telescopes and sensitive instruments can we begin to tease out their properties, how many stars they contain, how those stars move, and what lies hidden within their faint outlines. And despite their quiet appearance, ghost galaxies like Leo the First play an outsized role in galactic science. Their very existence challenges assumptions about what a galaxy is. Traditionally, galaxies were defined as large, luminous collections of stars. But Leo the First forces us to broaden that definition. Though it has few stars, it holds together with the help of a massive dark matter halo, which acts as scaffolding for the sparse stellar population. In this sense, Leo the First is a galaxy where the invisible outweighs the visible, a place where most of its mass cannot be seen. This disproportion between light and mass is perhaps one of the most extreme in known galactic systems. It raises fascinating questions. Why are galaxies like Leo the First so poor in stars? Did they lose their gas before they could form more? Were they stripped of material by the Milky Way? Or did they form this way, quiet, dim, and starved, from the very beginning? One hypothesis is that environmental effects, like ram pressure stripping or tidal disruption, may have removed Leo I's gas early in its history, halting star formation prematurely. Another idea suggests that Leo the First might have never accreted much gas to begin with, forming in a relatively barren pocket of the early universe. Both possibilities would explain its low star count and long dormancy. Yet, the fact that it contains a small fraction of younger stars suggests a more complex timeline, possibly including brief episodes of renewed star formation triggered by interactions or infall events. Its ghostly nature also makes Leo the First an important cosmological test case. Many simulations of dark matter structure formation predict the existence of hundreds or even thousands of faint satellite galaxies around a galaxy like the Milky Way. Yet, we observe only a few dozen. This discrepancy, known as the missing satellites problem, has puzzled cosmologists for years. Leo the First, as a real-world example of a low-luminosity, dark matter-dominated galaxy, helps bridge that gap. It proves that such systems do exist, but they're extremely hard to see. In this way, Leo the First becomes more than just a ghost. It becomes a whisper from the hidden universe, a message from the structure that doesn't shine. It tells us that the universe is likely filled with these shadowy companions, faint galaxies drifting undetected through the void, bound not by visible light but by gravity and dark matter. From the ground, Leo the First appears near the bright star Regulus in the constellation Leo, yet ironically, this proximity to such a luminous object is part of what made it so hard to detect. Regulus washes out the sky in its neighborhood, forcing observers to look away, right past the subtle light of Leo the First. There's a poetic irony to this, the brightest stars in the sky distracting us from the dimmest, the grand obscuring the quiet. And so Leo the First remains a kind of cosmic secret. It's a galaxy of silences, shadows, and suggestions, a structure that exists more in gravitational influence than in light. Yet, through persistent observation, sophisticated modeling, and a deepening understanding of galactic dynamics, we are beginning to bring its story into focus. The more we study Leo the First, the more we realize that brightness is not the only measure of importance. Some of the universe's most significant structures whisper instead of shout. They linger at the edges of vision, revealing themselves not through radiance, but through motion, mass, and mystery. Leo the First is one of those structures. A ghost, yes, but one whose haunting presence is teaching us to see the unseen, and listen to the quietest voices in the cosmos. To truly grasp how elusive Leo the First is, it helps to place it within the broader context of galactic astronomy. Among the known members of the Milky Way's galactic neighborhood, Leo the First remains one of the faintest galaxies ever identified, not because it is the smallest or farthest, but because it emits so little light per unit area that it blends almost seamlessly into the cosmic background. Its low surface brightness is so extreme that it effectively camouflaged itself for most of human history, hiding in plain sight against the deep canvas of the night sky. Even though Leo the First is relatively nearby, roughly 820,000 light-years from the Milky Way's center, it took until 1950 to be discovered. And that discovery didn't happen because of direct observation through a telescope. Rather, it was found on photographic plates, detected as a subtle enhancement of star counts in a region of the sky near the bright star Regulus, in the constellation Leo. The irony is palpable. A bright foreground star likely delayed our recognition of this faint background galaxy for decades. To understand why Leo I is so dim, consider its absolute magnitude, a measure of how bright it would appear from a standard distance. Leo I has an absolute magnitude of around -12, which is significantly fainter than even the smallest classical dwarf galaxies. For comparison, the Milky Way has an absolute magnitude of around -21, meaning it's more than 10 million times brighter in terms of total luminosity. And yet, Leo I isn't even the faintest satellite we've found. Other galaxies, like Segway 1 or Bodes 2, are even dimmer. But Leo I's combination of distance, faintness, and lack of structure makes it uniquely difficult to detect and study. The challenge is not just the faint light, it's the diffuseness of that light. A faint but compact object, like a distant quasar or compact dwarf, can still stand out against the sky. But Leo I is diffuse, meaning its stars are spread out over a relatively large area. That low surface brightness makes it incredibly hard to distinguish from the background noise of the sky. For decades, this made Leo I virtually invisible to surveys that relied on brightness thresholds or direct imaging. It wasn't until astronomers began to conduct deep, wide-field sky surveys that such faint galaxies started to appear in our data. Its detection represented a shift in how astronomers searched for galaxies. No longer could we rely solely on high-luminosity, high-contrast objects. Leo I forced a new kind of sensitivity, one that could detect subtle variations in star density, patterns that might suggest a hidden, extended structure. With this paradigm shift came a realization: Leo I is likely just one of many such ghostly galaxies lurking at the edges of visibility. Indeed, since the discovery of Leo I, dozens of other ultra-faint dwarf galaxies have been found orbiting the Milky Way, thanks to deep surveys like the Sloan Digital Sky Survey (SDSS), the Dark Energy Survey (DES), and the Pan-STARRS project. These galaxies often contain as few as a few hundred stars, and yet they are still gravitationally bound, likely held together by large amounts of dark matter. In many ways, Leo I was the gateway to this realization, that dark matter halos can host galaxies too faint to detect without highly sensitive techniques. This opens a floodgate of questions about how many such galaxies are out there, still hidden. The Milky Way's satellite system may include hundreds of faint dwarfs, most of which are simply too dim to be detected with current instruments. And Leo I's story suggests that even a galaxy with several million stars can be nearly invisible if those stars are old, faint, and sparsely spread. The fact that it took until the 1950s to discover such a nearby and relatively massive dwarf hints that we are only seeing the tip of the galactic iceberg. There's also a significant implication for cosmology. As mentioned earlier, the missing satellites problem, the mismatch between the number of dwarf galaxies predicted by simulations and those we observe, has long been a tension point in astrophysics. Leo I and other ultra-faint dwarfs provide evidence that the problem may not lie in the models, but in our incomplete observational capabilities. If galaxies like Leo I are common but hard to see, then many more could exist undetected, hiding near bright stars, behind dense fields of foreground stars, or simply below the surface brightness limits of current sky surveys. Furthermore, the fact that Leo I is one of the most massive of the faint dwarfs suggests it represents a transitional class of galaxy, massive enough to be interesting, faint enough to be overlooked, and uniquely positioned to challenge our definitions of what a galaxy even is. How faint can a galaxy be and still be considered a galaxy? Does it require a minimum number of stars? A minimum luminosity? Or is the presence of dark matter enough? Leo I tests the boundaries of these definitions. It forces us to reconsider how we categorize celestial objects. A few million old stars scattered sparsely across thousands of light years, orbiting the Milky Way on a high velocity, possibly unbound path. This hardly sounds like the classical image of a galaxy. And yet, Leo the First exhibits all the characteristics of one. It's gravitationally bound, it has a stellar population, it moves as a coherent unit, and it appears to be embedded in a massive dark matter halo. That qualifies it, even if its glow is too faint to notice without extraordinary effort. As we push the frontiers of observational astronomy with tools like the Vera-C Rubin Observatory, scheduled to come online in the near future, we may soon uncover a vast, previously hidden population of Leo I-like galaxies. These ghostly systems, scattered across the sky like faint fingerprints of dark matter, will offer new insights into galactic evolution, dark matter structure, and the early history of the universe. Leo I, then, is a pioneer. It was among the first of the modern era's faint galaxies to be revealed, a hint that the cosmos is more populated, more intricate, and far more subtle than we ever imagined. Its dimness is not a flaw or a curiosity, it is a clue. A clue that some of the universe's most essential truths may lie not in what shines, but in what barely whispers. Most satellite galaxies orbit their host in elongated ellipses, gently circling for billions of years in vast cosmic loops. But Leo I doesn't obey that familiar choreography. It seems to be blazing its own trail, a radical path that barely curves at all, plunging straight through the outer reaches of the Milky Way's gravitational influence like a comet slingshotting around the Sun. This makes Leo I's orbit not just unusual but extraordinarily rare. Among the dozens of known Milky Way satellites, almost none move the way Leo I does. It's on a trajectory that's nearly radial, perhaps even hyperbolic, raising the possibility that it's not bound to the Milky Way at all. To understand the peculiarity of Leo I's orbit, imagine watching a planet orbit the Sun. Most of the time, these orbits are nice ellipses, flattened circles that keep the object moving in predictable curves. That's how most satellite galaxies behave around the Milky Way. Dwarfs like the Sagittarius dwarf spheroidal galaxy or the Sculptor galaxy follow roughly elliptical orbits, spiraling in and out slowly over cosmic timescales. They're part of the Milky Way's extended family, locked in by gravity, making repeated passages around our galactic core. Leo I, by contrast, is more like a speeding bullet. Its orbit appears to be almost straight, a trajectory aimed directly inward or outward with minimal sideways motion. This is what astronomers call a radial orbit, meaning that most of the galaxy's motion is directed along a straight line from the center of the Milky Way, rather than moving sideways or in a circular path. If the Milky Way were a campfire, most satellite galaxies orbit around it like moths. But Leo I behaves more like a firework shot straight toward the flames before flying back out. Astronomers calculate the shape of such an orbit using a measure called eccentricity, where a perfectly circular orbit has an eccentricity of 0, and a highly elongated ellipse nears a value of 1. A radial orbit is at the extreme end, essentially approaching a straight line plunge. And if the eccentricity exceeds 1, the object is no longer on a closed orbit at all, it's hyperbolic, meaning it will pass by once and never return. That's the case with many comets visiting the inner solar system for the first and only time, and Leo I may be doing something similar on a galactic scale. The data on Leo I's velocity, especially from Hubble and Gaia, support this interpretation. The galaxy is moving nearly directly away from the Milky Way at high speed, suggesting it is on its outbound leg after a previous inward plunge. The timing and geometry imply it may have passed close to the Milky Way's center around 1 billion years ago, picking up speed during that close encounter before being flung back out into the galactic halo, or possibly into the intergalactic void. This differs dramatically from most other dwarfs, which show evidence of multiple passages, tidally induced star formation, and long histories of interaction. For instance, the Sagittarius dwarf galaxy has orbited the Milky Way several times, leaving behind streams of stars as it is gradually torn apart. Leo I, on the other hand, shows no clear tidal stream, no strong signs of past disruption, and no recurring pattern in its orbit. That's consistent with a first-in-fall scenario, in which Leo I has only recently arrived at the Milky Way, made a close approach, and is now on its way out, possibly forever. The radial nature of Leo I's orbit also means it would have spent very little time near the galactic center, which is rich in stars, gas, and tidal forces. This brief interaction could explain why Leo the First is still relatively intact. It didn't linger near the dense regions where many satellites are shredded by gravity. Instead, it likely plunged quickly through the galactic outskirts, where the gravitational field is weaker and the risk of disruption is much lower. But the most intriguing part of Leo I's orbit is the possibility that it's hyperbolic, meaning not just radial, but fast enough to escape. If its current speed relative to the Milky Way exceeds the escape velocity at its distance, it won't come back. That would make it the first confirmed satellite galaxy to escape from the Milky Way, an event rarely seen in galactic dynamics. Hyperbolic orbits are expected to be uncommon, especially among dwarf galaxies, because the process of capturing or binding satellites usually slows them down. A hyperbolic trajectory implies that Leo the First had either an enormous initial speed when it entered the Milky Way's sphere of influence, or it gained that speed through some extreme gravitational interaction, perhaps with the Milky Way's massive dark matter halo, or even another galaxy. Interestingly, cosmological simulations of galaxy formation suggest that radial and even hyperbolic orbits are more common in the outer reaches of large halos. When small galaxies fall into massive clusters or dark matter wells, their first approach is often radial. Over time, dynamical friction and gravitational torques can pull them into more circular orbits. But if a dwarf galaxy like Leo the First came in fast, on a narrow trajectory, and had enough mass to resist quick deceleration, it might maintain its original path and velocity. This kind of orbit carries implications not just for Leo I's fate, but for our understanding of the Milky Way's gravitational field. If Leo the First is truly on a hyperbolic path, then either the Milky Way is less massive than previously believed, or Leo the First had external forces accelerating it beyond what standard models predict. Either way, the galaxy's motion is rewriting our assumptions about how far the Milky Way's gravity can reach, and how often it might lose satellites to the cosmic wilderness. And there's one more wrinkle to this story. Leo I's orbit may be part of a larger pattern involving other dwarf galaxies. Astronomers have found tentative evidence that Leo the First, Leo the Second, and several other distant dwarfs may share similar orbital characteristics, possibly hinting that they entered the Milky Way together as part of a galactic group. In this scenario, Leo the First might not be an isolated outlier, but a member of a once-bound collection of galaxies disrupted during infall. The group could have been pulled apart by the Milky Way's gravity, with Leo the First flung outward while others settled into bound orbits, or were torn apart. Whatever the case, Leo I's orbital path stands as a cosmic anomaly, a sharp contrast to the swirling ballet of most Milky Way companions. It's not circling politely. It's tearing through the galactic stage like a renegade, dancing on the edge of gravity's grasp. Whether it's just visiting or making a final exit, Leo I's trajectory is a rare glimpse into the violent, chaotic undercurrent of galactic dynamics, a testament to the unpredictable forces shaping even the quietest, faintest galaxies in our universe. What if Leo the First was never truly part of the Milky Way's entourage at all? What if, rather than being a long-time satellite on an erratic orbit, Leo the First is actually a cosmic passerby, a galaxy just brushing against our own before hurtling off into the intergalactic void, never to return? This idea, known as the flyby hypothesis, is not only possible, it's becoming increasingly plausible based on Leo I's trajectory, velocity, and structural characteristics. In this scenario, Leo the First may be what astronomers call a first-in-fall system, or perhaps not even that, more like a cosmic tourist making a brief, gravity-guided detour through our corner of the universe. The concept of galactic flybys isn't entirely new. In simulations of structure formation on cosmological scales, flybys happen surprisingly often, especially in regions where dark matter halos brush up against each other in vast cosmic filaments. Not every object that comes close to a galaxy like the Milky Way is destined to stay. Some are moving too quickly, or at such an angle, that they never become gravitationally bound. They make a single close approach, gaining speed through gravitational interactions, and then escape forever. That's exactly the kind of story Leo the First seems to be telling. Its radial trajectory, plunging almost directly toward and then away from the galactic center, is atypical for bound satellites, which tend to have elliptical or rosette-like orbits. Combine that with its unusually high velocity, potentially exceeding the local escape velocity, and you have a strong case for a galaxy that's not on a long-term orbit, but a temporary visit. To support this idea, astronomers turn to detailed models of the Milky Way's mass and gravitational potential. If Leo I's speed is above the escape threshold for its distance, which is estimated to be near or slightly beyond 200 km per second, then it's not gravitationally bound. Even if its speed is near that threshold, its trajectory is so steep that it would take only a slight gravitational nudge, perhaps from another satellite galaxy or a dark matter substructure, to push it over the edge and free it from the Milky Way's influence. Interestingly, Leo I shows very few signs of tidal disruption, features like stellar streams, tidal tails, or warped structures that often appear when a dwarf galaxy is bound to and repeatedly orbiting a larger galaxy. This lack of distortion supports the idea that Leo I hasn't spent much time interacting with the Milky Way. If it has only recently arrived, or if it's not bound at all, then there hasn't been enough time for the Milky Way's tidal forces to significantly affect its structure. Leo I looks remarkably intact for a galaxy that's supposedly been near the gravitational heart of our galaxy. That alone raises eyebrows. In a broader cosmological sense, flyby galaxies like Leo I challenge our traditional view of satellite systems. For decades it was assumed that most small galaxies near a massive host were gravitationally bound. But more recent simulations, especially those incorporating realistic models of large-scale cosmic flows, suggest that a significant fraction of close proximity galaxies could be unbound interlopers, galaxies just passing through a larger system's halo. Flybys also have important implications for understanding galaxy assembly. If Leo I is a flyby, then it carries with it a record of a different history, possibly originating far from the Milky Way, shaped by its own unique environment, and on a path determined more by large-scale cosmic flows than by local gravitational interactions. It may have formed in a distant filament of the cosmic web, drifted for billions of years through low-density voids, and only now entered the vicinity of the Milky Way on its one and only visit. And this visit may not be casual. Even a single pass through the Milky Way's halo can leave a mark. If Leo I's trajectory took it through a dense region of the Milky Way's dark matter halo, it could have induced gravitational wake effects, ripples or disturbances in the Milky Way's own structure, especially in its dark matter distribution. Some studies suggest that fast-moving objects like Leo I could even affect the orbital behavior of other satellites, disturbing satellite planes, or contributing to the warping of the Milky Way's disk over long timescales. The flyby hypothesis also ties into another hot topic in astrophysics, the backsplash galaxy concept. In this idea, a galaxy once entered the gravitational boundary of a larger host like the Milky Way, passed through the inner regions, and then escaped, its speed now boosted by the gravitational slingshot. Backsplash galaxies are technically not current satellites, because they're no longer bound, but they carry chemical and dynamical signatures of past interactions. If Leo I is a backsplash galaxy, it may have briefly been a satellite a billion years ago, only to be flung outward during its first pericentric passage. This possibility aligns with some data suggesting Leo I passed near the Milky Way's center about 1 to 2 billion years ago, possibly accelerating due to gravitational interactions during that flyby. It may have picked up energy from the Milky Way's deep gravitational well, allowing it to reach its current high velocity. In that case, Leo I would be first in, first out, having made one close approach and now destined to drift into the deep intergalactic wilderness. Of course, determining definitively whether Leo I is bound or unbound isn't easy. It depends on many factors, including the total mass of the Milky Way, which is still under debate. If the Milky Way is more massive than some models suggest, it could still retain Leo I despite its high speed. But if the Milky Way is on the lighter side, especially in terms of its dark matter halo, then Leo I may indeed be slipping away. In either case, Leo I becomes a unique and valuable subject for study. If it's bound, it tells us something about the Milky Way's gravitational strength, and the extreme outer limits of its influence. If it's unbound, it tells us that our galactic neighborhood is more dynamic and open than we thought, that galaxies can drift in and out of one another's gravitational zones, leaving subtle imprints as they go. Ultimately, the flyby hypothesis transforms Leo the First from a passive satellite to an active participant in the Milky Way's story. It's not just a dim galaxy at the edge of our halo. It might be a messenger from the broader universe, offering a fleeting look at structures and histories beyond our own. And as it speeds away into the void, it leaves behind more than just questions. It leaves behind a trail of cosmic intrigue, a reminder that not all visitors stay, and not all galaxies are bound by gravity alone. While the flyby hypothesis paints Leo the First as a lone traveler merely passing through, there's another equally compelling possibility, one that casts Leo the First not as a visitor, but as a former resident, now ejected with extraordinary speed. This idea rests on a cosmic phenomenon known as the gravitational slingshot, or more formally, gravitational assist, a process well known in spacecraft navigation and increasingly recognized in galactic dynamics. It proposes that Leo the First may have once orbited the Milky Way, but something, perhaps a powerful gravitational interaction, hurled it outward on its current near-escape trajectory. In this version of events, Leo the First isn't a flyby. It's a fugitive. To understand how this might work, we must look at the underlying physics. A gravitational slingshot occurs when a smaller object, like a galaxy or spacecraft, passes close to a much larger moving body. If the geometry is just right, the smaller object can steal some of the orbital energy of the larger system, accelerating dramatically. We've used this technique with spacecraft many times. Voyager, Galileo, Cassini, all gained momentum from flybys of planets like Jupiter or Saturn to reach the outer solar system. The same rules can apply on a vastly larger scale. In Leo I's case, a gravitational slingshot might have occurred if it passed close to the Milky Way's dense inner halo, or even had a complex interaction with another massive satellite galaxy, such as the Large Magellanic Cloud, LMC. These interactions would have allowed Leo the First to pick up additional velocity, altering its original orbit from a closed elliptical path to one that is now nearly radial, perhaps even open, sending it away from the Milky Way forever. This scenario solves several puzzles. First, it explains why Leo the First is so fast. If it had been moving slowly through the galactic halo for eons, it shouldn't be accelerating now. But if it had a recent, close encounter with a dense gravitational region, say, within 50,000 light-years of the Milky Way's center, it could have received the extra push needed to reach escape velocity. Second, it accounts for its relatively intact structure. A galaxy that passed through the central regions too many times would be torn apart by tidal forces. But one with a single, close perigalactic passage might survive, just long enough to be flung away. Simulations of galaxy evolution support this idea. In high-resolution cosmological models, satellite galaxies often experience complex gravitational interactions, not only with their host galaxy but also with other satellites. These interactions, particularly three-body encounters, can redistribute momentum and energy in unexpected ways. For example, if Leo the First once shared a common orbit with another dwarf galaxy, and the two had a near collision while near the Milky Way's center, one could be slowed and captured, while the other, Leo the First, could be flung outward. This is the classic slingshot mechanism, a chaotic dance that trades binding energy for momentum. Another possible mechanism involves the Large Magellanic Cloud, which is not just a passive satellite but a massive, fast-moving galaxy in its own right. With a mass possibly exceeding 100 billion solar masses, the LMC has enough gravitational heft to noticeably perturb the Milky Way's own halo. Recent studies show that the LMC is dragging the Milky Way's center of mass toward it, warping the halo, and possibly altering the orbits of nearby satellites. If Leo the First passed near the LMC, or if the LMC passed near Leo the First, the interaction could have resulted in a gravitational assist, redirecting Leo I's orbit and giving it the momentum to leave. There's also the matter of timing. Based on current measurements, Leo the First likely made its closest approach to the Milky Way about 1 to 2 billion years ago. This aligns well with the gravitational slingshot event. That epoch also happens to be the period when the LMC was beginning its own inward plunge into the Milky Way's halo. If the two galaxies interacted near that time, the encounter could have altered Leo I's trajectory dramatically. While exact modeling of this interaction is difficult, early simulations suggest that such a gravitational slingshot is possible, especially given the LMC's mass and relative motion. Importantly, Leo I doesn't exhibit the kind of stellar debris or tidal tails we'd expect from a galaxy undergoing prolonged disruption. This supports the idea that any gravitational slingshot it experienced was quick and energetic, rather than gradual. The briefness of the event would have allowed Leo I to remain mostly intact, carrying its ancient stars and dark matter halo along for the ride as it was ejected outward. This hypothesis also carries deeper implications for our understanding of galactic evolution and interaction. If Leo I was ejected by gravitational interactions, then the Milky Way is not just passively collecting satellites, it's actively expelling them. The idea of galactic ejection challenges traditional hierarchical models where large galaxies simply grow by accreting smaller ones. It suggests that our galaxy might also lose mass over time, not just gain it. Moreover, if Leo I can be slingshot out, then other satellites could as well. There may be dozens of galaxies that were once part of the Milky Way, now drifting through intergalactic space, dark, faint, and disconnected, like cosmic castaways. Finding them would be exceedingly difficult, but Leo I could be the first identified example of a galaxy undergoing such a fate. And if true, this makes Leo I a kind of celestial fossil, carrying with it clues about the Milky Way's gravitational structure and interaction history. Its trajectory may help map the mass distribution in our galaxy's halo, constrain the mass of the LMC, and illuminate the complex gravitational ballet that plays out between host galaxies and their satellites. In that sense, Leo I's escape becomes more than an anomaly. It becomes a probe, a tool for unraveling the invisible architecture of our galactic environment. Its path through space, precise and perilous, may have been shaped not by chance but by violent encounters and gravitational negotiations, culminating in its present course, a high-speed departure, its destiny altered by a single moment of cosmic turbulence. And as it recedes, Leo I carries with it the gravitational fingerprint of its past, evidence that galaxies can be not just born and bound, but flung away, their lives forever reshaped by the massive hands of the cosmos. Leo I, despite its ghostly appearance and sparse population, holds within it a surprisingly intricate story of stellar evolution, a tale etched into the faint glimmers of light emitted by its ancient stars. At first glance, Leo I might appear to be a galaxy frozen in time, composed almost entirely of aged, red stars, silent witnesses to the earliest epochs of the universe. But as astronomers peered closer, they uncovered a narrative with more complexity than expected, a galaxy that not only formed stars in the ancient past but experienced unusual episodes of star formation, including some as recently as a few billion years ago. This anomalous history makes Leo I not just dim, but deeply intriguing. In dwarf spheroidal galaxies like Leo I, star formation typically occurred rapidly in the early universe, within the first few billion years after the Big Bang. The initial bursts of star formation created massive, short-lived stars that exploded as supernovae, enriching the surrounding gas with heavier elements. After that brief but energetic beginning, most of these galaxies exhausted their gas or had it stripped away, ending star formation and leaving behind only old, metal-poor stars. For decades, Leo I was assumed to follow this same pattern. However, more recent and high-resolution photometric studies, using powerful instruments like the Hubble Space Telescope and the Very Large Telescope, began to tell a different story. These telescopes resolved individual stars in Leo I, allowing astronomers to build detailed color, magnitude diagrams, charts that plot the brightness and color of stars, revealing their age and composition. The result was surprising. While Leo I's stellar population was indeed dominated by ancient stars aged 10 to 13 billion years, there was clear evidence of intermediate-age stars, stars that formed between 1 and 7 billion years ago, long after the initial burst of star formation had supposedly ended. Even more remarkably, there is evidence of stars younger than 2 billion years, and some possibly less than 1 billion years old. This is almost unheard of in a classical dwarf spheroidal galaxy so distant from the galactic center. For comparison, many other satellites, like the Sculptor or Draco dwarfs, ceased forming stars over 10 billion years ago and have remained dormant since. Leo I defies that trend. Why did Leo I continue forming stars long after its peers went dark? One explanation lies in its isolation. Unlike many other satellite galaxies that orbit close to the Milky Way and suffer from tidal stripping and environmental quenching, Leo I is located far on the outskirts of the halo. This distance, over 250,000 light-years from the galactic center, may have shielded it from the disruptive forces that stripped other dwarfs of their star-forming gas. In this relative quiet, Leo I may have been able to retain or reacquire enough gas to continue forming stars intermittently, even late into its life. There's also the possibility that Leo I's unusual orbit played a role. If, as hypothesized, it had only a single close passage near the Milky Way's core about 1 billion years ago, that event might have actually triggered a final burst of star formation by compressing the gas within Leo I. Close interactions with the Milky Way's gravity could have generated tidal forces strong enough to squeeze Leo I's internal gas reservoirs, causing it to collapse and form new stars in a brief final wave of activity. The presence of these younger stars has been confirmed not only through photometry but also through spectroscopic analysis, which measures the light from individual stars to determine their metallicity, that is, the abundance of elements heavier than helium. Young stars typically show higher metallicities because they form from gas enriched by generations of earlier supernovae. In Leo I, a gradient emerges. Older stars have extremely low metal content, suggesting they formed from primordial material, while the younger population exhibits a slightly higher metallicity, consistent with later, recycled star formation. Interestingly, Leo I's chemical enrichment history also suggests that the galaxy underwent a delayed or prolonged star formation epoch, possibly influenced by supernova feedback. After the initial starburst, massive stars exploded, ejecting gas and halting star formation temporarily. But without strong external influences, like ram pressure stripping or nearby galactic winds, Leo I may have slowly cooled and retained enough material to reignite its star-forming core. This episodic history of star formation points to a more self-regulated internal evolution rather than externally driven quenching. Leo I may have gone through multiple pauses and restarts, forming stars in irregular bursts whenever conditions allowed. The youngest stars found in Leo I may have formed in one of these brief resurgences, possibly linked to environmental triggers like the gravitational slingshot mentioned earlier, or mild gas accretion from the cosmic web. In total, the star formation history of Leo I is now understood to be bimodal or even multimodal, consisting of an early dominant epoch followed by a long, quiet tail of sporadic formation. While the bulk of its stellar mass originated over 10 billion years ago, somewhere between 10% and 20% of its stars formed after that initial epoch, many in the last few billion years, a surprisingly high fraction for such a faint, low-mass galaxy. These findings make Leo I stand out not only in brightness and velocity, but also in stellar demographics. It is a galaxy that somehow avoided the galactic extinction experienced by its peers. It maintained the ability to form stars far longer than expected, despite its modest mass and proximity to a much larger galaxy. This extended star formation may also relate to the amount of dark matter Leo I possesses. If it is indeed embedded in a massive dark matter halo, that could help explain its ability to retain gas over long timescales and avoid being disrupted. Ultimately, Leo I's star formation history reveals it to be not a fossil, but a survivor, a galaxy that continued to grow and evolve in subtle ways, long after others had gone silent. In its dim light lies a record of persistence, a quiet chronicle of stellar birth under the most fragile and isolated of conditions. And perhaps this is the most fascinating truth of all, that even in the cold, empty reaches of the halo, far from the galactic plane and cut off from the richness of the Milky Way's star-forming regions, a tiny, dim galaxy like Leo I could find the strength to spark new light, long after the rest of the universe had written it off. The faint glow of Leo I may suggest quietude, but hidden within that silence are echoes of explosive events that shook its structure and forged the heavy elements now traced in its stars. These are the remnants of ancient supernovae, massive stellar deaths that occurred billions of years ago, leaving behind faint chemical scars that offer rare and powerful insight into both Leo I's star formation history and its mysterious dark matter content. For a galaxy as small and faint as Leo I, the detection of even a handful of supernovae is a monumental discovery. Given its relatively modest stellar population, likely no more than a few million stars in total, it has produced far fewer massive stars than a galaxy like the Milky Way. Yet, over its extended history of intermittent star formation, Leo I still managed to form enough massive stars to trigger multiple generations of supernova explosions. These catastrophic deaths enrich the surrounding interstellar medium with heavy elements, providing astronomers with a chemical trail that can be read like a fossil record. Unlike in large galaxies, where supernova remnants can often be directly imaged in radio or X-ray wavelengths, Leo I is too faint, too distant, and too low in interstellar gas to retain the visible wreckage of ancient supernovae. Instead, astronomers study chemical abundances in its stellar populations, looking specifically at metallicity patterns in the stars that formed after the explosions. Elements like iron, Fe, magnesium, Mg, calcium, Ca, and titanium, Ti, serve as indirect but reliable signatures of past supernova activity. In Leo I, spectroscopy reveals a wide range of metallicities, especially among its older stars. Some contain only trace amounts of iron, suggesting they formed in a near-pristine environment, perhaps before any supernovae had occurred. Others, particularly stars formed in the intermediate age population, show higher metallicity levels, pointing to later star formation enriched by the products of earlier supernovae. What's most telling, however, is the pattern of these elements. Type II supernovae, which arise from the collapse of massive stars, produce large quantities of alpha elements like magnesium and calcium. Type I supernovae, white dwarf explosions in binary systems, tend to occur later in a galaxy's history and contribute significant amounts of iron. In Leo I, scientists observe a clear shift in elemental ratios over time, indicating that both types of supernovae occurred. The older stars have high alpha to iron ratios, typical of early enrichment dominated by Type II supernovae. But in younger populations, the alpha element abundance drops while iron increases, marking the delayed contribution of Type I events. This transition is a critical clue. It suggests that Leo I was able to retain supernova ejecta long enough for these heavy elements to be recycled into new stars, a feat that would be impossible if the galaxy were not held together by a substantial gravitational potential. For a low-mass dwarf spheroidal galaxy, this kind of metal retention is usually only possible if the system is embedded within a massive dark matter halo. In fact, this chemical evidence is one of the strongest indirect arguments in favor of Leo I containing a large ratio of dark matter to baryonic matter. Without dark matter, the energy from the first few supernovae would have blown the galaxy's gas away entirely, halting star formation and preventing further enrichment. The fact that Leo I shows signs of supernova activity spanning billions of years implies that it had enough gravitational binding energy, most likely supplied by dark matter, to hold on to its gas reservoir despite the energetic violence of stellar death. Some models even suggest that Leo I may have had more supernovae than expected for a galaxy of its size, potentially due to a top-heavy initial mass function in its earliest stellar generations, meaning it formed more massive stars than average, increasing the likelihood of early supernovae. This might explain the strong early chemical enrichment seen in its oldest stars, as well as the presence of more intermediate-age stars than typical for dwarfs in its class. Beyond chemical traces, supernovae may have played another role in Leo I's evolution, regulating its star formation over time. The energy injected into the interstellar medium by these explosions could have heated the remaining gas, suppressing further star formation until the gas cooled and recondensed. This cyclical process of feedback, explosions triggering quiescence, followed by cooling and new star formation, is likely what led to Leo I's bursty, uneven star formation history. Without sufficient dark matter, the first feedback cycle would have been the last. Additionally, simulations show that in small galaxies like Leo the First, supernova-driven winds can expel a significant fraction of the galaxy's gas if not tightly bound. The fact that Leo the First retained enough gas to produce stars for billions of years suggests that supernova winds were contained, again hinting at a massive, extended dark matter halo cushioning the effects of feedback. The velocity dispersion of Leo I's stars, how fast they move relative to one another, also supports this idea. The stars move faster than one would expect if the galaxy's gravity were supplied only by visible matter. The implication: there's a lot of invisible mass keeping Leo the First together. And here lies an even deeper mystery. If Leo the First really is escaping the Milky Way's gravity, as some models suggest, then its dark matter halo must have played a role in powering that escape. The energy required to accelerate a galaxy to the Milky Way's local escape velocity is immense. Yet Leo the First, despite its faintness, may have had enough internal gravitational cohesion, thanks to its dark matter, to survive that journey intact. The supernova evidence, then, becomes more than just a record of stellar death. It becomes a clue to the dynamical fate of the entire galaxy. These ancient explosions, brief, luminous, and long gone, are now merely inferred through their chemical fingerprints. But their legacy endures. They enriched the stars we observe today, shaped the interstellar medium of Leo the First, and provided indirect proof that this seemingly fragile galaxy is, in fact, deeply anchored by an unseen mass. In a cosmic sense, the supernovae of Leo the First serve not only as creators of heavy elements, but as witnesses to dark matter's grip, silent validators of a force we cannot see, yet whose presence echoes through every generation of stars. Though Leo the First resides on the fringe of the Milky Way's immense halo, its journey through space has not been entirely peaceful. The quiet, isolated dwarf spheroidal galaxy may appear structurally intact at first glance, but a deeper examination reveals subtle yet significant clues that Leo the First has been, and perhaps still is, under the influence of powerful gravitational forces. These clues come in the form of its stretched stellar distribution, faint signs that suggest Leo the First is experiencing tidal interactions as it navigates the complex gravitational field of our galaxy. Tidal interactions occur when the gravitational pull of a massive galaxy like the Milky Way exerts uneven forces on a smaller galaxy like Leo the First. The side of the dwarf closer to the Milky Way experiences a stronger pull than the far side, creating a tidal gradient. Over time, this difference in gravitational force can begin to stretch and distort the satellite galaxy, drawing stars away and producing elongated stellar structures, tidal tails, or even complete disintegration. In Leo I's case, direct visual signs of destruction are not as obvious as in more heavily disrupted satellites like the Sagittarius dwarf galaxy, which has left behind long streams of stars tracing its past orbits. However, the evidence for tidal interaction in Leo the First lies not in grand arcs of stripped stars, but in more subtle distortions, measurable irregularities in its shape, stellar kinematics, and density profile. One of the key indicators comes from deep photometric imaging. When astronomers map the positions of stars in Leo the First, especially with wide-field telescopes sensitive to extremely faint features, they find that the galaxy is not perfectly spherical, as one might expect in a dynamically relaxed system. Instead, Leo the First exhibits a mild ellipticity, a stretched-out form that could be the result of tidal forces pulling it along the direction of its motion. This elongation aligns suspiciously well with the galaxy's trajectory, suggesting that what we're seeing may not be an intrinsic feature of Leo the First, but a consequence of its interaction with the Milky Way's tidal field. Adding to the picture is Leo I's stellar density profile. Normally, in a gravitationally stable dwarf spheroidal galaxy, the density of stars falls off smoothly and predictably with distance from the center, forming a roughly exponential, or king profile. But Leo I's outer stellar halo doesn't behave quite so neatly. Observations reveal a flattening and asymmetry in the outskirts, with star counts remaining higher than expected in certain directions, especially toward the Milky Way. This could indicate tidal debris, stars that are in the process of being stripped from the galaxy but have not yet fully separated into a distinct stream. Furthermore, there's the issue of velocity dispersion among Leo I's stars. When astronomers measure how fast stars are moving within the galaxy, they find a distribution that's broader than would be expected from the visible mass alone. While this is often attributed to dark matter, it could also reflect the influence of external tidal heating, a phenomenon where gravitational interactions stir up stellar motions and artificially inflate the velocity spread. In other words, some of Leo I's stars might be moving more chaotically not because of dark matter, but because they're being shaken loose by tidal forces. This possibility is supported by simulations. In computational models that recreate the orbits and structures of satellite galaxies under the influence of a massive host, tidal features like those seen in Leo I are common in systems that are either on their first close approach or in the process of escaping. Leo I's high velocity, radial trajectory, and extended stellar envelope are all consistent with such a scenario. Interestingly, while Leo I doesn't have dramatic tidal tails like Sagittarius, some studies suggest that it may possess a low surface brightness halo of extratidal stars, a fuzzy, ghostly population of stars just outside its traditional boundary, gradually drifting away. These stars are not tightly bound to the galaxy anymore but haven't yet formed a coherent stream. They're like mist trailing behind a fast-moving object, evidence that Leo I may be just beginning to unravel as it flees the gravitational grip of the Milky Way. Another clue comes from the direction of its motion. Leo I is moving almost directly away from the center of the Milky Way, and this trajectory aligns with the axis of its elongation. If it is being stretched, it's being stretched along the path it's traveling, consistent with a galaxy that's being pulled apart as it leaves. This kind of alignment is rare in stable, bound systems but very common in galaxies undergoing tidal disruption. Yet for all these signs, Leo I remains remarkably intact, suggesting that if tidal forces are at work, they're only beginning to take hold. Perhaps Leo I's dense dark matter halo has helped shield it thus far, keeping the core of the galaxy together even as its outer stars begin to feel the Milky Way's tug. Or perhaps Leo I has simply not been close enough, or long enough, to experience the full destructive power of tidal stripping. If it is truly on an escape trajectory, then its most intense tidal encounter may already be behind it, leaving it damaged but not destroyed. Still, the implications are fascinating. If Leo I is showing early signs of tidal disruption, then continued observations may reveal a progressive unraveling in the years or decades to come. Future surveys, especially those using next-generation telescopes like the Vera C. Rubin Observatory, may detect even fainter stellar debris, subtle distortions, or faint star streams that further confirm Leo I's slow disintegration. But even in its current state, Leo I offers a vivid snapshot of what happens when the immense tides of galactic gravity begin to tear at a smaller system. It is a natural laboratory for studying the balance between dark matter, stellar dynamics, and tidal forces, where each star drifting from its parent galaxy carries with it a story of motion, tension, and cosmic reshaping. In this context, Leo I is not simply a runaway galaxy. It is a galaxy in transition, caught in the act of being unbound, its stellar distribution stretching out like fingers grasping at the void, reaching backward toward the galaxy it is leaving behind. Whether it ultimately flies free or falls apart, Leo I is teaching us something profound about the limits of galactic cohesion, how even in the vast loneliness of intergalactic space, gravity still writes the fate of stars. Leo I exists in a peculiar place among the many dwarf galaxies orbiting, or once thought to orbit, the Milky Way. While it shares some common characteristics with its galactic peers, a closer examination reveals just how different it really is. When compared to other known dwarf satellites like Leo II, Sculptor, or the Sagittarius dwarf galaxy, Leo I begins to stand apart, not just in motion, but in composition, structure, history, and destiny. Let's begin with one of its closest neighbors in name and apparent sky location, Leo II. Like Leo I, Leo II is a dwarf spheroidal galaxy. The two lie relatively near each other in the sky, both in the direction of the constellation Leo, and both were discovered around the same mid-20th century timeframe. But the similarities end there. Leo II is significantly fainter and smaller than Leo I, with a far more relaxed internal structure and lower velocity relative to the Milky Way. Its orbit is more circular and well within the bounds of gravitational capture, whereas Leo I's trajectory may already be breaching those bounds. Leo 2's star formation history is more typical of a dwarf spheroidal, an initial burst of star formation followed by long dormancy. It lacks the younger stellar population seen in Leo I, suggesting it may have been quenched earlier, either through internal feedback or environmental stripping. Then there's the Sculptor dwarf galaxy, another classical dwarf spheroidal, located in the constellation Sculptor in the southern sky. It lies closer to the Milky Way than Leo I and is better studied thanks to its proximity. Sculptor shares Leo I's status as a low luminosity, dark matter-dominated system, but in almost every other way, the two are opposites. Sculptor's stellar population is older, with nearly all of its stars forming more than 10 billion years ago. Unlike Leo I, Sculptor shows no evidence of intermediate age or young stars. It appears to have undergone a single early epoch of star formation and then quickly ceased, likely due to the loss of its gas, possibly stripped away by the Milky Way's hot halo or blown out by internal supernovae. Its velocity is moderate, its orbit relatively stable, and its structure undisturbed, suggesting a long-term, low-energy relationship with the Milky Way. It is, in many ways, what astronomers expect from a classical satellite galaxy. Now contrast this with Leo I, which behaves less like a satellite and more like an intergalactic interloper. Its extended star formation history, its high radial velocity, its possible unbound orbit, these make Leo I stand out. While Sculptor and Leo II look like fossils of early galactic assembly, Leo I looks like an active participant in a current dynamic process, whether that's an escape, a recent infall, or the result of a slingshot interaction. One of the most dramatic comparisons, however, comes when we look at the Sagittarius dwarf spheroidal galaxy, SGR-DSBH. Sagittarius is perhaps the most famous of the Milky Way's satellites, not because of its age or size, but because it is actively being torn apart by tidal forces. Discovered relatively late, in the 1990s, it was found practically underneath the Milky Way's disk, hidden behind dense clouds of stars. Since its discovery, Sagittarius has become a model for how galaxies are shredded by their host. Long streams of stars, stretching tens of thousands of light-years, now arc around the Milky Way in complex loops, tracing the past orbits of Sagittarius over multiple passages through the galactic halo. This is tidal disruption at its most extreme, and it paints a sharp contrast with Leo I. While both galaxies may be experiencing the Milky Way's gravitational pull, Sagittarius is far closer, and has likely completed multiple orbits, each one peeling away more of its stars. Leo I, on the other hand, appears largely intact. There are hints of distortion and signs of gravitational influence, but no tidal tails like those seen in Sagittarius. If Leo I has been near the Milky Way only once, or if it's just now on a departure trajectory, then it hasn't suffered the same fate. Structurally, Sagittarius is also more massive in terms of stellar content, yet it may be less tightly bound overall, which made it more vulnerable to disruption. Leo I's relatively compact stellar core and potentially more massive dark matter halo may have allowed it to resist disruption even as it entered the Milky Way's gravitational influence. Another interesting comparison lies in metallicity and star formation patterns. Sagittarius, despite being heavily disrupted, shows a range of stellar ages, including young and intermediate-age stars, much like Leo I. This is unusual among classical dwarf spheroidals, and may point to a shared resistance to early quenching. Both galaxies formed stars over extended periods, suggesting they either retained gas longer than expected or had access to external reservoirs that allowed rejuvenation. However, Sagittarius did this within the inner halo of the Milky Way, where tidal forces eventually caught up. Leo I did it from farther away, more isolated, and possibly on its way out before disruption could complete. Then there's the broader class of dwarf spheroidal galaxies like Draco, Ursa Minor, and Sextans, which are some of the most dark matter-dominated and least luminous galaxies known. These systems often lack gas entirely, have extremely old stars, and show little dynamical complexity. They seem to have frozen in place billions of years ago. Compared to these, Leo I is practically vibrant, more massive, more active, historically, and kinematically bolder. It retains signs of internal complexity, motion, and evolutionary change that these ultra-faint dwarfs lack. Lastly, Leo I differs in how it challenges our assumptions about galactic boundaries. Most satellite galaxies are expected to orbit safely within the confines of their host's halo. Leo I dares to test those limits. Its potential to break free of the Milky Way, while others like Sculptor or Leo II remain bound, makes it not only exceptional among its peers but possibly unique within the local group. If it escapes, it would become one of the first observed examples of a galaxy transitioning from satellite to free-floating dwarf, revealing new dimensions of galactic evolution. In essence, Leo I is a dwarf galaxy that refuses to conform. Where others are quiet, it is active. Where others are slowly torn apart, it speeds away. And where others seem bound to their hosts by ancient gravitational contracts, Leo I may be tearing up the agreement, writing a new script of galactic autonomy, propelled by physics and history into the uncharted dark. To truly understand a galaxy like Leo I, a faint, distant, and fast-moving outlier, astronomers must rely not only on telescopic observation, but on the remarkable predictive power of computational modeling. In fact, it's only through sophisticated simulations that we've been able to grasp the true extent of Leo I's anomalous motion, reconstruct its possible history, and peer into its likely future. Observations give us the snapshots, but simulations let us press play on the cosmic timeline, offering insights into where Leo I came from, what it's doing now, and where it's headed in the vast dark of intergalactic space. Simulating Leo I begins with what we know: its current position, distance from the Milky Way, radial velocity, proper motion, as best we can measure it, and its estimated mass. By plugging these values into numerical models governed by Newtonian gravity and general relativity, researchers can reconstruct Leo I's orbital path backward and forward in time. These simulations must account not only for the gravity of the Milky Way, but also for contributions from the dark matter halo, nearby satellite galaxies, the Large Magellanic Cloud, LMC, and the gravitational dynamics of the local group at large. One of the first surprises that came out of these simulations was that Leo I's motion doesn't conform to what we'd expect from a bound satellite. Early models assumed that Leo I, like most dwarf spheroidal galaxies, was gravitationally tethered to the Milky Way in an elliptical or circular orbit. But once better proper motion data from the Hubble Space Telescope and later Gaia mission were incorporated into the simulations, the picture changed dramatically. Leo I's orbit appeared radial, plunging inward toward the Milky Way's core before veering sharply away again, implying a single close encounter, not a repeating one. This trajectory hinted at a scenario astronomers refer to as a first-in-fall or possibly a flyby event, meaning Leo I may have entered the Milky Way's halo only once, perhaps just a few billion years ago, and is now on an outbound trajectory so fast it may never return. The velocity data, approaching 200 km per second relative to the galactic center, is key here. When this figure is plugged into escape velocity models of the Milky Way, Leo I's energy budget hovers precariously near or even slightly above the gravitational binding energy required to remain a satellite. In multiple simulations, Leo I crosses the threshold, drifting further and further outward with time, slowly evaporating from the Milky Way's grasp. But simulations also offer more than a binary, bound or unbound, answer. They allow scientists to explore many possible orbits by tweaking initial conditions within the margin of observational uncertainty. These Monte Carlo-style simulations test thousands or even millions of potential trajectories, revealing not just one possible fate for Leo I, but a probability cloud of futures. Some trajectories show it slowing down and falling back toward the Milky Way in a few billion years. Others show it arcing outward forever, ultimately becoming an intergalactic rogue. Further simulation layers include dynamical friction, a drag force that slows massive objects as they move through dark matter halos. If Leo the First is embedded in a massive enough dark matter halo of its own, it will experience more friction, potentially slowing it down enough to remain bound. But if it's less massive than we estimate, or if the Milky Way's dark matter halo is less dense than assumed, Leo the First might experience minimal friction and simply slip away. Some models also account for the gravitational tug of the Large Magellanic Cloud, which is itself a massive satellite galaxy currently falling into the Milky Way. In certain simulations, the LMC's movement warps the Milky Way's own dark matter halo, distorting the potential well and nudging nearby satellites. If Leo the First passed near the LMC at the right moment, it could have received a gravitational assist, boosting its speed and altering its orbit, a cosmic slingshot encoded in the simulations. This interaction has been shown to nudge satellite trajectories significantly, and Leo the First is one of the few candidates that may have experienced such a high-energy encounter. Simulations have also begun to incorporate baryonic physics, the behavior of normal matter like gas, stars, and supernova feedback. These processes can affect a galaxy's ability to resist tidal forces or retain mass. When included, such simulations help test hypotheses about Leo I's extended star formation history. For example, if Leo the First had a late burst of star formation triggered by a paracentric passage near the Milky Way, a good simulation should reproduce that behavior under realistic conditions. The fact that several models do gives weight to the theory that Leo the First may have passed close enough to the galactic center to compress its gas, ignite new star formation, and then begin its escape. But simulating Leo the First is not only about where it goes, it's also about what happens to it on the way. Tidal stripping, heating, and dark matter loss can be tracked through these models. In some simulations, Leo the First begins to unravel, shedding outer stars as it moves outward. In others, it remains surprisingly intact, protected by a dense core of dark matter. Observationally, we don't yet see strong evidence of a stellar stream trailing Leo the First, but if simulations predict one, future telescopes like the Nancy Grace Roman Space Telescope or the Vera C. Rubin Observatory may be able to detect it. Even more exciting is the potential to use Leo the First as a test particle to map the structure of the Milky Way itself. Because its motion is so extreme, Leo the First is exquisitely sensitive to the total mass and shape of the Milky Way's halo. By tweaking simulation parameters until Leo I's observed motion matches the predicted outcome, astronomers can place constraints on the size, shape, and density of our galaxy's dark matter envelope. Some studies suggest that if Leo the First is truly unbound, then the Milky Way's halo may be less massive than once believed, which would have ripple effects on our understanding of galaxy formation throughout the universe. In essence, simulating Leo the First is like holding a key to a much larger puzzle. It's not just about understanding one dwarf galaxy, it's about using that galaxy to decode the invisible scaffolding of the cosmos. Every change in Leo I's path reflects a deeper truth about gravity, structure, and interaction on galactic scales. As simulations grow more complex and data from future missions refines Leo I's measurements, we'll be able to peer with ever greater clarity into this galaxy's past and project with confidence the outcome of its cosmic journey. In the end, simulations allow us to glimpse what the naked eye never could, the story of a faint, ancient traveler either tearing free from our galactic family or orbiting for the last time before vanishing into intergalactic space. Through equations and code, Leo the First becomes more than a distant speck of stars. It becomes a living model of the universe's most fundamental forces at play. Of all the questions orbiting Leo the First, the most electrifying remains this: could it escape? Could this dim, ancient, and seemingly fragile dwarf spheroidal galaxy actually break free from the gravitational grip of one of the largest galaxies in the universe? It's not just a curiosity. It's a question that, if answered, could reshape our understanding of galactic dynamics, satellite systems, and the true nature of dark matter. And as the evidence accumulates, the answer is increasingly tilting toward yes. At the heart of this question lies a deceptively simple principle: escape velocity. In basic terms, if Leo the First is traveling faster than the escape velocity of the Milky Way at its location, some 820,000 light-years, or about 250 kiloparsecs, from the galactic center, then it's on an unbound orbit and will never return. But calculating escape velocity isn't straightforward. It depends on the mass distribution of the Milky Way, especially the dark matter halo, which is both enormous and invisible. Estimates of the Milky Way's total mass vary widely, ranging from as low as 500 billion to as high as 2 trillion solar masses. That's a significant spread, and Leo I happens to sit right on the edge of the uncertainty. The most recent measurements of Leo I's velocity come from a combination of Gaia data, which gives proper motion, sideways movement across the sky, and spectroscopy, which gives radial velocity, motion toward or away from us. When combined, these measurements suggest that Leo I is traveling at around 198 to 210 kilometers per second relative to the Milky Way's center of mass. That figure by itself is staggering. For a galaxy of Leo I's size and location, this is the fastest known radial velocity of any Milky Way satellite. In fact, some studies suggest it's the fastest ever measured for any known dwarf galaxy associated with the Milky Way. To assess whether that speed is enough to escape, astronomers modeled the Milky Way's gravitational potential based on different assumptions about its total mass. In many of these models, especially those at the lower end of the Milky Way mass estimates, Leo I is already past the local escape velocity. In other words, if the Milky Way is closer to 1 trillion solar masses or less, Leo I is likely unbound. It's moving too fast to be held in orbit, and is currently on an escape trajectory that will carry it into intergalactic space. But if the Milky Way is more massive, closer to 1.5 or 2 trillion solar masses, then Leo I might still be bound, just barely. In that case, its trajectory is more like that of a comet, extremely elongated, stretched across hundreds of thousands of light years, but still gravitationally tethered. It might slow down, curve back around, and return over the course of tens of billions of years. However, simulations suggest that even in high-mass Milky Way scenarios, Leo I's energy budget places it right at the threshold. It may be gravitationally bound in theory, but effectively free in practice, traveling so far, for so long, that it might never meaningfully interact with the Milky Way again. Adding to this escape hypothesis is the direction of Leo I's motion. Unlike most dwarf galaxies that move in elliptical or circular paths around the Milky Way, Leo I's orbit is nearly radial. It appears to be headed almost directly away from the galactic center, consistent with a galaxy that made a single plunge inward and is now flying outward on a hyperbolic trajectory. This shape is not typical of long-term satellite orbits. Instead, it fits the profile of an object that may have been captured briefly, or passed close to the Milky Way once, and is now departing. This notion is reinforced by simulations that trace Leo I's motion backward in time. In many of them, Leo I is shown to have entered the Milky Way's halo only once, within the last 2 billion years, before slingshotting away. That would make it a first-in, first-out object, a galaxy that was never deeply embedded in the Milky Way's gravitational potential. This challenges our assumption of Leo I as a long-term satellite and suggests it might instead be a cosmic interloper, temporarily influenced by our galaxy's gravity but not fundamentally tied to it. Moreover, the lack of extensive tidal features around Leo I may further support this idea. If Leo I had been orbiting the Milky Way for billions of years, we would expect to see clear tidal tails, similar to those observed in the Sagittarius dwarf galaxy and others. But Leo I remains largely intact. While there are hints of distortion, there's no unmistakable evidence of long-term gravitational stripping. This suggests that if Leo I was influenced by tidal forces, it was likely during a single, relatively recent flyby, not repeated orbits. There's also the matter of timing. The apparent age of some of Leo I's youngest stars, formed perhaps as recently as 1 to 2 billion years ago, matches up intriguingly well with its supposed paracentric passage near the Milky Way. It's possible that the compression of gas during this close encounter triggered a final burst of star formation, before Leo I began its escape. If true, this would be yet another data point confirming the idea that Leo I is no ordinary satellite. It's a galaxy that was shaped by a brief but transformative interaction with the Milky Way. Yet caution remains. the full three-dimensional motion of Leo I is not completely pinned down. Gaia provides some proper motion, but uncertainties remain, and even small changes in the measured trajectory could shift the balance between bound and unbound. Additionally, the Milky Way's own mass is still being debated. Until both the galaxy's mass and Leo I's motion are better constrained, the case remains probabilistic, not definitive. Still, the bulk of evidence leans heavily in favor of escape. Multiple independent studies, based on different datasets, simulation methods, and theoretical assumptions, have converged on the same conclusion: Leo I is most likely not gravitationally bound to the Milky Way anymore. If that's true, it would be the first confirmed satellite galaxy in the process of escaping a large host galaxy, an extraordinary discovery in the context of galactic evolution. And perhaps most compelling of all is what this means for our understanding of galactic boundaries. Leo I challenges the notion of satellites as static members of a galactic family. It suggests instead that galactic systems are more dynamic, their populations not fixed, but constantly in flux. Galaxies can fall in, interact, and move on, like dancers in a slow, gravitational ballet. Leo I may be the first we've caught in the act of leaving. In a universe where the dance of gravity binds stars, gas, and dark matter together in complex webs of interaction, Leo I is a rare moment of release, a cosmic fugitive breaking away from the gravitational bonds that defined its past. The Milky Way, for all its grandeur, may be watching one of its oldest companions quietly slip away. The potential escape of Leo I from the Milky Way is not just a curiosity, it's an astronomical anomaly of profound significance. In the vast expanse of the cosmos, galaxies are pulled into clusters, caught in halos, and locked into orbits that last billions of years. The local group, our own neighborhood of galaxies, is a relatively compact region of the universe comprising over 80 known members, including the Milky Way, Andromeda, and their numerous satellite systems. Among all these, the possibility that Leo I might be on its way out, actually escaping the gravitational pull of its host, marks a deeply rare event, one that challenges the prevailing understanding of how galaxies interact, evolve, and are retained within large gravitational systems. To appreciate why Leo I's possible departure is so extraordinary, we need to consider the nature of galactic retention. Massive galaxies like the Milky Way and Andromeda reside at the centers of deep gravitational wells, surrounded by immense dark matter halos. These halos stretch for hundreds of thousands, sometimes millions, of light years, encompassing vast regions of space where gravity still dominates. Dwarf galaxies within this range, like Leo II, Sculptor, Draco, and Carina, are usually captured by this gravity early in cosmic history. Once drawn in, they typically remain as permanent satellites, slowly orbiting their host, subjected to tidal stripping and dynamical friction, but seldom escaping. It's like water spiraling down a drain. Rarely does a droplet gain enough speed to reverse course and fly back up. Indeed, among the dozens of satellites orbiting the Milky Way, virtually all are on closed orbits, some more elliptical than others, some slightly tilted, but all fundamentally bound. Observations and models of the local group over the past decades have reinforced this idea, that once a galaxy enters the gravitational influence of a larger one, it stays. Occasionally, tidal forces may disrupt it or strip away its stars, but actual escape is nearly unheard of. It's the same across the universe. Galaxy clusters trap hundreds or thousands of galaxies in complex gravitational webs, and only under rare circumstances does one break free. So why is escape so rare? One reason is the enormous escape velocity required. A galaxy on the outskirts of the Milky Way, say, 250 kiloparsecs from the center, would still need to be traveling at over 180 to 200 kilometers per second to fully break away. That kind of velocity is uncommon, especially for dwarf galaxies that typically orbit more slowly. Moreover, any dwarf galaxy entering the Milky Way's halo would almost immediately begin to lose energy through dynamical friction and tidal interactions, making it even harder to attain the necessary escape speed. Another reason is that in hierarchical cosmology, the model by which galaxies form and grow through mergers and accretion, dwarf galaxies are expected to be captured, not expelled. The idea of a satellite galaxy naturally gaining enough speed to escape flies in the face of this structure. So when a candidate like Leo I is found, moving at breakneck speed and potentially on an unbound orbit, it raises fundamental questions. Is it a statistical outlier, a 1 in a billion fluke? Or are we finally detecting a class of galaxies we've been missing all along? Leo I may be the first such case we've observed clearly, but simulations of galactic formation do suggest that unbound or nearly unbound galaxies can occur. In large-scale cosmological simulations like Illustris, Apostle, and Elvis, researchers have identified small satellite galaxies that make single flyby passages of larger galaxies and are then flung out, never to return. These are rare, comprising just a few % of all satellite interactions, but they do exist. What's remarkable about Leo I is that it may be the first real-world observational confirmation of this theoretical possibility. And it's not just any dwarf. Leo I is among the most massive classical dwarfs known to orbit the Milky Way. Its high radial velocity, low tangential motion, extended star formation history, and near radial trajectory all align with the profile of a galaxy on its first and last pass. And crucially, this movement is not just theoretical. The data from Gaia's precise astrometry, combined with Hubble's long baseline proper motion studies, provide strong kinematic evidence that Leo I is on a hyperbolic or near-parabolic orbit, one that leads out, not back. If this is confirmed in full, Leo I becomes a prototype, the first dwarf galaxy caught in the act of exiting a galactic system, in real time, within the local group. And its uniqueness doesn't end there. The local group is not a chaotic tangle of galaxies flinging around at random, it's a relatively settled region, dominated by the Milky Way and Andromeda, whose mutual gravitational attraction is drawing them slowly together. In this environment, where most motion is toward coalescence, an object flying away is dramatically out of place. There's also the added implication that we might be underestimating how many galaxies are on similar escape paths. If Leo I was faint enough to evade confident analysis for decades, how many other small, fast-moving galaxies might have gone undetected altogether? Perhaps some passed close by the Milky Way eons ago and were launched outward, now floating in intergalactic space, silent relics of gravitational encounters long past. Detecting them would require surveys of very faint, high-velocity galaxies well beyond the Milky Way's halo, something the upcoming Nancy Grace Roman Space Telescope and Rubin Observatory may make possible. Leo I may also prompt a reevaluation of the definition of satellite galaxies. If satellites can come and go, captured temporarily by a host and then slung outward, then the traditional classification of bound satellite must be refined. Perhaps we need a new category: transient satellites, galaxies that appear, interact, and leave within the lifespan of a galaxy like the Milky Way. That would have implications for how we model mass assembly, galactic interactions, and even the shape of the cosmic web. And what about Andromeda, the Milky Way's larger neighbor? It too has its own retinue of satellites, and similar high-velocity dwarfs have been identified on its outskirts. Studies of M31 suggest that some of its satellites may also be on first and fall or escape trajectories, echoes of the dynamic processes now being glimpsed in Leo I. In this light, Leo I's possible escape is not just an isolated event, it is a revelation, a signal that our understanding of galactic ecosystems is still evolving. The laws of gravity remain the same, but the behaviors that emerge within those laws, especially in the presence of complex, asymmetric dark matter halos, are far richer than once thought. So in the stillness of space, a faint smudge of stars is fleeing. Perhaps it's alone. Perhaps it's the first of many. But in either case, Leo I is carving a new path in astronomy, turning our gaze not just inward toward the gravitational embrace of galaxies, but outward, toward the rare, escaping few that show us the universe is never as static as it seems. Leo I's flight through the outer reaches of the Milky Way's halo is more than just a fascinating journey for a lone dwarf galaxy. It's a powerful cosmic probe, a rare messenger carrying information about the very nature of our own galaxy. In the absence of visible boundaries or structures, one of the few ways to determine the true extent, shape, and mass of the Milky Way is to watch how other objects move around it. And Leo I, with its astonishing speed and near-escape trajectory, acts like a thrown stone that reveals the shape of the gravitational pond it's trying to leave. At the core of this inquiry lies the question, how massive is the Milky Way really? Despite centuries of studying our galaxy, we don't have a precise answer. That's because the vast majority of the Milky Way's mass, up to 90% or more, is invisible, locked away in a dark matter halo that stretches far beyond the luminous disk of stars and gas we see in the night sky. We can't observe this halo directly, so we rely on dynamical tracers like Leo I to estimate its properties. The galaxy's speed, direction, and orbital behavior all act as indirect measurements of the Milky Way's gravitational field. If Leo I is indeed unbound, if it is moving faster than the escape velocity at its current location, then the mass of the Milky Way must be less than previously assumed. Many traditional models have placed the total mass of the Milky Way in the range of 1.3 to 2 trillion solar masses, including both baryonic, normal, matter and dark matter. These estimates are consistent with keeping even fast-moving dwarfs like Leo I tethered. But if Leo I is getting away, that implies the gravitational grip of the Milky Way isn't as strong at large distances as those models would suggest. In other words, Leo I may be telling us that the Milky Way's halo is either less massive or less concentrated than we thought. This would mean revising the standard mass model downward, possibly toward 800 billion to 1.2 trillion solar masses, placing the Milky Way at the lower end of mass estimates compared to similar spiral galaxies. This has profound implications, not just for our own galaxy, but for galaxy formation models across the cosmos. If the Milky Way is less massive, it may have had a quieter merger history, retained fewer satellites, and had lower star formation efficiency compared to more massive counterparts like Andromeda. It also changes our perspective on the local group's dynamics. The gravitational tug-of-war between the Milky Way and Andromeda, two giants set on a collision course, is sensitive to each galaxy's mass. A less massive Milky Way might mean the eventual collision with Andromeda is slower, happens later, or occurs off-center. The entire orbital choreography of the local group is recalibrated when one of its lead dancers, especially the Milky Way, is lighter than expected. But Leo I's implications go even deeper. By moving at near-escape velocity and possibly exiting the halo, it forces us to reconsider the shape and symmetry of the Milky Way's dark matter envelope. Most simplified models assume the halo is spherical or mildly oblate, an even distribution of mass extending outward in all directions. But real galaxies, especially those that have absorbed smaller galaxies over time, are rarely so clean. The path of Leo I may suggest that the Milky Way's halo is asymmetric or lopsided, perhaps shaped by interactions with other large satellites like the Large Magellanic Cloud, LMC. In fact, some simulations have shown that the infall of the LMC, a galaxy with a mass of up to 200 billion solar masses, can warp the Milky Way's halo, shifting its center of mass and distorting its gravitational influence. If Leo I passed near this warped region or through a lower density corridor in the halo, it may have been able to build up enough velocity to escape. This means Leo I might be doing more than tracing the halo's edge. It could be mapping its internal structure, telling us where the dark matter is more or less dense, where the gravitational terrain slopes downward or flattens out. These subtle gravitational gradients are impossible to measure with starlight alone, but Leo I's motion cuts through them like a high-speed scanner. There's also the matter of halo truncation. If Leo I truly escapes, it might be because the Milky Way's halo has a finite extent, a kind of gravitational edge, beyond which the mass density drops rapidly. While dark matter halos are theoretically infinite, in practice, the effective reach of a galaxy's gravity diminishes. Leo I could be helping to define that edge, showing us where the gravitational influence begins to weaken significantly. This has direct implications for how we define membership in a galaxy. Is Leo I still part of the Milky Way family? Or has it already stepped outside the bounds? Additionally, Leo I's trajectory is prompting astronomers to rethink the motions of other satellite galaxies. If one dwarf can escape, might others be on similar paths? Some galaxies at the fringe of the halo, like Tucana 3 or Crater 2, also exhibit odd motions that may suggest non-standard orbits. If Leo I is the first observed escapee, it might not be the last. Its case could prompt a reanalysis of the entire satellite system, looking for more outliers. And then there are the deeper theoretical implications. Leo I offers a test case for the cold dark matter (CDM) paradigm. This dominant cosmological model predicts certain behaviors for satellite galaxies, including retention in halos, certain orbital characteristics, and responses to tidal forces. If Leo I's motion turns out to be inconsistent with CDM expectations, it could hint at new physics, perhaps warm dark matter, modified gravity, or unseen interactions at large scales. It's a long shot, but such anomalies are precisely where breakthroughs in cosmology are born. From another angle, Leo I's movement might also help us test the role of cosmic environment. Is the Milky Way part of a larger gravitational flow or structure, a filament of dark matter, or a region of underdensity that affects how satellites come and go? Leo I could be a product of not just local gravity, but large-scale structure dynamics that extend well beyond the halo. Finally, on a philosophical level, Leo I challenges the notion that galaxies are gravitationally eternal companions. If a satellite galaxy, born or captured billions of years ago, can one day gather enough momentum to flee its host, then the cosmic story is less static than we thought. Galaxies can evolve not only internally, but in relation to one another, drawing close, influencing, and separating again. Leo I's potential escape marks such a turning point, not just in its own history, but in our understanding of what the Milky Way really is. So as Leo I hurtles outward, it leaves behind more than just distance. It trails a string of questions, models, and recalibrations, each one forcing us to look more closely at the massive, invisible structure we call home. It is a faint galaxy on the edge of perception, but in its motion, it illuminates the invisible. If Leo I truly leaves the Milky Way for good, if it escapes the vast gravitational pull of our galaxy and continues its solitary trek into the intergalactic dark, it will mark not just a physical departure, but a symbolic and scientific one as well. The act of escape isn't merely about motion, it is a boundary-crossing event that reshapes how we view galactic families, gravitational ties, and the cosmic balance of forces. So what happens if Leo I escapes? To begin with, the most immediate implication is the loss of a long-studied satellite galaxy, one that has been crucial to understanding dark matter, galactic formation, and the dynamics of satellite systems. For decades, Leo I has served as a sort of galactic benchmark, one of the classic dwarf spheroidal galaxies orbiting the Milky Way, often used in comparative studies alongside Leo II, Sculptor, and Fornax. It's been part of the reference set we use to explore galaxy evolution in low-mass systems. If Leo I is no longer gravitationally bound to us, then it technically no longer belongs to the Milky Way system, and that changes its role in comparative research. In some ways, we lose a sibling, cosmically speaking. But the consequences go far deeper than classification. Leo I's departure would become one of the few observed cases of a galactic escape, a rare and precious phenomenon that would be studied intensely for decades. Astronomers would monitor it with growing interest, trying to capture as many details as possible before it becomes too distant and faint to study in depth. We would be watching in near real time as a galaxy transitions from satellite to intergalactic wanderer, something never directly observed before. It becomes not just an object of loss, but one of extraordinary value. From a theoretical perspective, Leo I's escape forces us to re-examine the gravitational balance of the Milky Way. While the galaxy itself will not lurch or shudder from the exit of a dwarf galaxy, it is far too massive for that. The departure of Leo I still subtracts from the total mass and momentum within the halo. Over billions of years, if more galaxies like Leo I exit, it could indicate that the Milky Way is shedding mass, particularly from its outskirts. While not immediately destabilizing, This gradual erosion might change how the Milky Way interacts with nearby systems, especially the approaching Andromeda galaxy. In this sense, Leo I's departure could also help map the outer edges of the Milky Way's gravitational boundary. Right now, those borders are vague and theoretical. We don't have an exact line that says, "Beyond this point, the Milky Way's gravity no longer rules." But if Leo I escapes, it helps draw that line more clearly. We could begin to think of galactic halos not as static fields but as zones of influence that evolve, shrink, and grow depending on mass flow, mergers, and cosmic interactions. There's also the question of gravitational balance among the local group. The local group is a system of more than 80 galaxies, with the Milky Way and Andromeda as its dominant members. If Leo I escapes the Milky Way, where does it go next? Will it drift endlessly through space, or will it eventually fall under the gravitational pull of another structure, like Andromeda or the broader gravitational field of the local group itself? If Leo I becomes unbound from us but not from the local group, it may still be recaptured, perhaps by another galaxy, or it might become one of a growing number of intergroup galaxies, either here nor there, but caught in the vast void between giants. In terms of research opportunities, Leo I's escape also opens up a whole new kind of case study. Instead of viewing it as a member of a closed system, scientists would now study it as a test particle moving through the broader cosmic web. Its motion could be used to probe the intergalactic medium, dark matter filaments, or even the gravitational tide of the local group as a whole. It becomes a free-moving laboratory, no longer constrained by the tides and torques of a central host galaxy. Its stars, gas, and trajectory would reveal what happens to a dwarf galaxy in true isolation, free from stripping, heating, and external forces. From a cosmological standpoint, Leo I's escape might be seen as a natural stage of galaxy evolution that we've simply failed to notice until now. After all, if galaxies can be captured and accreted, through mergers or infall, then they must also be capable of escape. Perhaps Leo I is showing us that galactic systems are more fluid than static, and that the so-called boundaries of a galaxy like the Milky Way are really permeable membranes, shifting and adjusting over cosmic time. Of course, the escape also raises philosophical questions. What does it mean for a galaxy to belong to another? Is membership defined by gravity alone? Or by history, interaction, or proximity? Leo I has spent eons near the Milky Way, formed stars, experienced tidal forces, and perhaps even triggered activity within our halo. If it now escapes, does that sever its identity as a satellite? Or does its legacy remain, no matter how far it drifts? From the human perspective, there's a certain poetry in Leo I's escape. A ghostly, nearly invisible dwarf galaxy, filled with ancient stars and wrapped in dark matter, slipping silently out of our galactic domain. It reminds us that the cosmos is dynamic, not fixed. Even the grand architecture of galaxies is in motion, changing, breaking, escaping. It humbles our assumptions of permanence. And yet, the escape is not necessarily the end. Leo I may drift far, but its data will remain with us. The information we gather now, its internal velocity dispersion, its star formation history, its total mass and dark matter profile, will continue to inform our understanding of galaxy evolution long after it fades beyond visibility. It becomes part of our scientific legacy, even as it slips from view. There's even the faint possibility that Leo I's escape could have long-term ripple effects. If its gravitational pull was interacting with other satellites, nudging them, aligning them, or creating resonances, its absence might destabilize or shift those structures. It's like removing a node from a complex web. The strands may not break, but they may certainly shift. So in the end, if Leo I leaves, it becomes more than a runaway. It becomes a trailblazer. The first known galaxy to leave the Milky Way's embrace not in violent collision, but in subtle, relentless drift. It becomes a signpost of cosmic transition, a reminder that even galaxies, ancient and gravitationally bound, can change their course and write new destinies. Leo I's dramatic escape from the Milky Way may not be an isolated incident. It could be the first visible tip of a much deeper current flowing through the galactic halo. As astronomers track the movement of satellites within the Milky Way's sphere of influence with increasing precision, an urgent question arises. Could others follow? Are there dwarf galaxies already slipping through the cosmic cracks, racing toward the edge, gaining enough velocity, and quietly preparing their exit? It turns out, Leo I might not be entirely alone in its rebellious trajectory. Other satellites within the Milky Way's halo are now under scrutiny, their motions re-examined through the lens of Gaia's unprecedented astrometric data. For decades, the assumption has been that satellite galaxies were more or less permanently captured, gravitational prisoners orbiting their massive host. But that assumption, much like Leo I's classification as a stable satellite, is beginning to crumble. A key example is Tucana 3, an ultra-faint dwarf galaxy discovered in 2015. Located over 25,000 light-years from the galactic center, Tucana 3 is among the smallest and dimmest dwarfs ever found. What makes it interesting is not just its tenuous hold on cohesion, but its elongated stellar stream, a clear sign that it's being torn apart by tidal forces. While it's currently within the Milky Way's halo, some orbital models suggest it could be on an extremely eccentric trajectory, possibly one that might eventually take it beyond the galactic boundary. Tucana 3 is likely not escaping yet, but it is being disrupted so significantly that future ejection is not unthinkable. Then there's Crater 2, another ghostly and diffuse galaxy discovered in 2016. Its size, stretching over 7,000 light-years, and incredibly low surface brightness make it almost invisible, yet it harbors a surprisingly calm internal velocity dispersion. This suggests either an unusual dark matter distribution or that it is in a transitional phase, either on its first infall, or already exiting the halo after a long, quiet journey inward. Its motion, while slower than Leo I's, is still under study, and there remains the tantalizing possibility that Crater 2 is also in a barely bound or even unbound orbit, one shaped by a recent close encounter. Leo II, Leo I's nearby neighbor in the sky, but not necessarily in 3D space, has also been flagged as a potential candidate for reclassification. Though not as fast or as far-flung as Leo I, its proper motion suggests a very elliptical orbit, and some models predict it may be on its first infall, just brushing past the Milky Way for the first time. If so, it may eventually follow a similar path, moving away after a single passage, depending on the depth of its plunge and the shape of the Milky Way's dark matter halo. And then there's the case of the Sagittarius dwarf galaxy, one of the most studied satellite galaxies in the sky. Sagittarius is unmistakably bound at present, but its multiple plunges through the Milky Way's disk over the past several billion years have torn it apart, leaving behind a massive tidal stream that wraps around the galaxy. Some parts of this stream have reached such great distances and are moving at such high velocities that segments of it may no longer be gravitationally bound. In this way, Sagittarius may be in the process of ejecting material, flinging stars and dark matter out of the Milky Way, even if the core of the dwarf galaxy itself remains trapped. But perhaps the most intriguing possibilities come from statistical outliers hidden in Gaia's ocean of data, small, dim galaxies that haven't been fully classified or whose motions are just now being charted. Some of these may turn out to be hypervelocity dwarfs, rare, fast-moving galaxies with peculiar orbits, some of which might be on escape trajectories, or just passing by, never truly captured at all. These are galaxies that might have been flung in our direction by past interactions with other groups, or ejected from other galactic systems, or are simply transient visitors in the local group. Beyond satellites, astronomers have also identified a growing population of hypervelocity stars, individual stars moving fast enough to escape the Milky Way entirely. Some of these are believed to have been ejected by interactions with the supermassive black hole at the center of the galaxy. If individual stars can be flung outward with such force, it opens up the possibility that entire dwarf galaxies could, under rare circumstances, experience similar slingshot-like acceleration. One potential mechanism for such acceleration is galactic three-body interactions. When two galaxies pass close to a third massive object, like the Milky Way or the Large Magellanic Cloud, gravitational energy can be transferred, boosting one object outward while the others continue in a different direction. Leo I's trajectory, for instance, may have been influenced by such an encounter, and other dwarfs might be in similar dynamical situations, gaining energy from cosmic pinball events before being nudged over the escape threshold. And speaking of the Large Magellanic Cloud, LMC, this massive satellite, potentially with up to 1/4 the mass of the Milky Way, may itself be distorting the shape of our galaxy's halo. The LMC's motion is dragging dark matter behind it in a kind of gravitational wake, and that dynamic shift could alter the escape velocity threshold in specific directions. In some regions, the LMC's influence might lower the escape barrier, making it easier for nearby dwarfs to slip away. This dynamic halo model could explain not just Leo I's trajectory, but also predict where future escapees might emerge. It's also worth considering that some galaxies may already be far beyond the Milky Way, previously bound but now unobserved escapees. These may be intergalactic dwarfs, tiny galaxies now drifting alone in the local group, too faint to be detected, but once part of a larger halo structure. Future telescopes like the Vera C. Rubin Observatory and Nancy Grace Roman Space Telescope could be crucial in locating these ghosts, faint, fast-moving galaxies on the edge of detection, slipping silently into the void. Ultimately, Leo I may not be a unique rebel but rather the first confirmed pioneer of a much larger phenomenon. The outer halo of the Milky Way is less a cage and more a porous boundary, with galaxies arriving, lingering, and perhaps even departing again. If so, the population of Milky Way satellites is not a closed book, it's an active, breathing system, with galaxies entering and exiting on billion-year timescales. This concept would revolutionize how we understand galactic life cycles, the behavior of dark matter halos, and the dynamics of the local group. It implies a kind of celestial migration, where galaxies don't merely form and stay put, but roam, interact, and sometimes move on, like celestial nomads in an ever-changing gravitational landscape. So while Leo I may be the first to capture our attention, it likely won't be the last. Eyes are now turning to the other quiet companions at the edge of our galaxy, asking not if, but who's next? Leo I's extraordinary motion across the vastness of space has forced astronomers to pause and reevaluate something once thought to be stable and well-defined, the boundaries of a galaxy. In textbooks and scientific models, galaxies are often depicted as coherent, self-contained structures, gravitational islands of stars, gas, and dark matter, each wrapped in a well-defined halo. But Leo I, with its near-escape trajectory from the Milky Way, exposes the illusion in that simplicity. It invites a profound rethinking of what we actually mean when we describe a galaxy's domain. For decades, the term galaxy implied a kind of sovereignty, a system of stars and matter held together by a shared gravitational fate, existing independently of its surroundings unless explicitly interacting or merging. This sense of galactic territory was extended to the idea of satellite systems, smaller galaxies trapped in the gravitational grasp of a larger host, forming part of its extended structure. Leo I has long been considered one of these satellites, a member of the Milky Way's galactic family. But if it's not bound, if it's moving fast enough to escape, then it challenges the assumption that being near a galaxy means being part of it. This matters because galactic boundaries are not drawn with visible lines. There is no cosmic fence separating the Milky Way from the rest of the universe. Instead, what we call the edge of a galaxy, particularly for systems dominated by dark matter, is a mathematical construct, often defined in terms like the virial radius, or R200, referring to the distance at which the average density of a galaxy's halo is 200 times the critical density of the universe. But even these metrics are theoretical and based on idealized models of spherically symmetric, isotropic mass distributions. Real galaxies, especially ones like the Milky Way with a rich history of mergers, satellites, and internal asymmetries, are far messier. Leo I's orbit, which is nearly radial and possibly hyperbolic, slices through this idealized framework like a blade. It does not loop gently or align with the orbits of most known satellites. Instead, it appears to have come in fast, from a great distance, and is now heading back out, potentially never to return. This alone raises a critical question. Can a galaxy be called a satellite if it's only passing through? If the gravitational encounter is temporary, or if the object was never truly captured, does it still count as part of the system? More than a semantic issue, this has real implications for how we study galaxy formation and structure. Observational catalogs often classify satellite galaxies based on position, not velocity. If a dwarf is close enough, say, within 300,000 light-years, it may automatically be grouped as a Milky Way satellite. But Leo I shows that location isn't enough. Without understanding a galaxy's full three-dimensional motion, especially its radial and tangential velocity, we risk misclassifying objects that are not gravitationally bound. That's not just a taxonomical error, it distorts our understanding of the Milky Way's mass, halo shape, and the behavior of its satellite system. Leo I compels a shift from a static definition of galactic domains to a dynamical one rooted in motion, history, and gravitational binding energy. The true boundary of a galaxy, in this view, isn't a hard edge or a fixed radius. It's a gradient, a region where gravity slowly yields to the broader tides of the universe. Galaxies are no longer sovereign fortresses, but open systems, leaking stars, absorbing dwarfs, and occasionally ejecting them too. This also impacts how we model the evolution of structure in the universe. In the hierarchical model of galaxy formation, small galaxies merge into larger ones, feeding growth. But if some dwarfs can resist capture or escape post-interaction, then the net mass gain of galaxies over time may be lower than expected. Galaxy halos may be more porous and fluid, more like eddies in a cosmic stream than the solid spheres we've assumed them to be. The concept of transient satellites emerges here, galaxies that are not bound indefinitely, but only for a fraction of cosmic time. These objects might interact gravitationally, trigger starbursts or tidal disruptions, and then slip away, never to be seen again. Leo I may be the first such example we've been able to track in real time, but simulations suggest it is not unique. Others may already have passed through and vanished, leaving behind only their gravitational echoes. And what of dark matter, the invisible scaffold around which galaxies form? If the Milky Way's dark matter halo is less massive or less symmetric than previously modeled, as Leo I's motion may suggest, then our picture of the galaxy's domain becomes even more complicated. The edge of the Milky Way may not be a clean sphere, but a lumpy, shifting border shaped by cosmic infall, past mergers, and the motion of nearby galaxies like the Large Magellanic Cloud or even Andromeda. This redefinition also touches on the concept of cosmic belonging. If Leo I isn't truly part of the Milky Way, then what is it? A free-floating member of the local group? A galactic refugee? Or does it belong to some larger, invisible structure, a filament or subhalo that we haven't yet detected? Perhaps we need a new category for such objects, intermediate galaxies, either fully satellite nor fully independent, moving through the interstices of gravitational regimes. The implications ripple outward. If Leo I redefines the Milky Way's domain, then similar questions apply to Andromeda, Triangulum, and other large galaxies. What are the true extents of their gravitational reach? How many of their supposed satellites are actually just passing by? And are some galaxies we've considered isolated actually former satellites, long since escaped? Even the classification of the local group itself might need revision. If member galaxies like Leo I are on temporary sojourns through a shared gravitational well, then the local group is not a static assembly but a fluid zone of influence, shaped by constantly shifting orbits and evolving boundaries. It's not a cosmic city of fixed addresses, but a roaming caravan of galaxies, sometimes converging, sometimes drifting apart. At its heart, Leo I's challenge to galactic boundaries is a challenge to simplicity. It reminds us that the universe is not cleanly sorted. It is not easily partitioned. It is a dynamic, turbulent, often ambiguous space, where galaxies don't just exist, but move, interact, and escape. And in that motion, they write the true shape of their domains, not in lines drawn on a map, but in the invisible curvature of gravity itself. Leo I's possible escape from the Milky Way isn't just a local anomaly, It's a tantalizing glimpse into a broader and rarely observed phenomenon: galactic fugitives. These are galaxies, stars, and massive systems that, through a combination of gravitational interactions, tidal forces, or cosmic slingshots, are flung from their home galaxies and launched into the wider cosmos. They are wanderers, no longer bound to any single galactic master, moving freely across the vast voids between structures. And although Leo I may be one of the first such events we've observed up close, the universe is likely teeming with such cosmic runaways. Throughout the universe, we have growing evidence, both observational and theoretical, that entire galaxies can and do escape their hosts. Often, these events are hidden from view. The galaxies involved may be too faint, too distant, or moving in directions difficult to trace. But in recent decades, thanks to deep surveys, simulations, and improved motion tracking tools, a pattern is beginning to emerge. One of the clearest examples outside our local group comes from the Virgo cluster, a massive cluster of galaxies about 65 million light-years away. This region is rich with galaxies of all sizes, spirals, ellipticals, dwarfs, and irregulars, moving under the collective gravitational influence of the cluster's deep potential well. Observations have shown that some dwarf galaxies in the outskirts of Virgo exhibit radial velocities and trajectories suggesting they are no longer gravitationally bound to any particular large galaxy. Instead, they are being flung out into intergalactic space, cast-offs from past gravitational interactions between much more massive systems. These dwarf galaxies are often victims of tidal stripping, where one galaxy gets too close to another and begins to lose its outer stars, gas, and even dark matter to the more massive partner. In extreme cases, this interaction doesn't just rob the smaller galaxy of material, it can completely eject the core of the dwarf itself, sending it flying out of the host's gravitational field. Sometimes, what's left behind are stellar streams, curved ribbons of stars and gas stretching tens of thousands of light-years, marking the path of the escaping body. Then there's the phenomenon of backsplash galaxies, objects that have already passed through the dense environment of a cluster and are now moving back out toward the cosmic outskirts. These galaxies are thought to be on highly eccentric orbits, their velocities close to or even exceeding the escape velocity of the cluster. They have experienced intense gravitational compression, bursts of star formation, or even near destruction, and now they carry those scars as they retreat into the cosmic wilderness. Some may never return, becoming intercluster wanderers, cut loose from any dominant structure. A compelling subset of these are recoiling galaxies, rare cases in which galaxies experience a dramatic change in motion due to the merger of supermassive black holes at their centers. When two black holes spiral into one another and merge, the resulting black hole can emit gravitational waves asymmetrically, creating a recoil effect that actually kicks the black hole, and potentially its host nucleus, out of the galaxy entirely. If the force is strong enough, this recoil can dislodge the entire central core of a galaxy, propelling it into intergalactic space. Though this phenomenon is mostly theorized and simulated, astronomers have identified a few candidates for such events: compact galaxies with off-center black holes or stripped cores moving at high velocities, that may be real-world examples. In even more extreme cases, entire galaxies have been observed traveling at hypervelocity speeds. One famous candidate is the galaxy 3C186, located about 8 billion light-years away. At its core lies a quasar, an incredibly bright, active galactic nucleus. The core appears to be displaced from the rest of the galaxy, possibly indicating a black hole kicked out by gravitational wave recoil. The velocities involved, thousands of kilometers per second, suggest this could be a hypervelocity galaxy core, flung from its original position and now hurtling through the intergalactic medium. Meanwhile, in galaxy clusters like Coma and Able 1689, deep imaging has revealed intergalactic light, diffuse starlight that doesn't belong to any galaxy but instead floats freely between them. This light is believed to originate from stars stripped from galaxies that were ejected, further supporting the idea that whole galaxies, or pieces of them, are frequently flung from their homes. These stars become part of what's called the intracluster light, a ghostly reminder of the violence of past interactions. Hypervelocity galaxies, though rare, also offer a compelling avenue for studying the large-scale structure of the universe. If a galaxy is escaping from its host or even a cluster, it can act as a test particle moving through the gravitational contours of cosmic filaments, voids, and superclusters. By tracking these rogue galaxies, astronomers hope to map the invisible scaffolding of dark matter that governs the movement of all cosmic structures. Even closer to home, our understanding of the Magellanic Clouds, the Large and Small Magellanic Clouds, two of the Milky Way's most massive satellites, is undergoing revision. Recent research suggests that the LMC may be on its first infall, and that it could eventually escape the Milky Way if not captured completely. Its enormous mass means it carries substantial momentum, and its influence on the Milky Way's dark matter halo has been enough to shift our galaxy's center of mass. While not currently escaping, the LMC's trajectory is another sign that galactic interactions are not always permanent. In the distant future, depending on gravitational interactions with the Milky Way and Andromeda, the LMC itself could become an intergalactic wanderer. And in the realm of stars, the evidence is even stronger. Hypervelocity stars, often traveling at several hundred kilometers per second, are constantly being discovered within the Milky Way. Many of these stars were likely ejected by close encounters with Sagittarius A, our supermassive black hole, or from binary disruptions during supernovae. Some of these stars are on escape trajectories, destined to leave the galaxy forever. If such events can fling stars, then with the right dynamics, such as three-body interactions, whole galaxies could experience the same fate. Simulations of cosmic evolution support this notion. In large-scale cosmological models, galaxy halos frequently experience flyby events, where smaller galaxies enter a larger halo, interact gravitationally, and then exit on an altered course. These simulated fugitives match what we might expect from objects like Leo I, galaxies that never truly settled into orbit, but instead were briefly caught before escaping back into intergalactic space. So Leo I, though unique in its clarity and proximity, is part of a much wider galactic diaspora. Across the universe, galaxies and their fragments are constantly shifting, merging, escaping, and dispersing. The idea that galaxies are permanent residents of a gravitational home is giving way to a more dynamic vision, one where migration is natural, where ejection is possible, and where the universe is filled with the echoes of past gravitational encounters. These galactic fugitives remind us that gravity is not always a binding force, it can also liberate. And when it does, it creates a rare and remarkable class of objects, solitary travelers that carry the signatures of their origins but are no longer tethered to them. Leo I may be just one such traveler, but it opens the door to a deeper understanding of galactic motion, cosmic history, and the invisible gravitational pathways that connect everything in the cosmos. The mystery of Leo I's origin casts a long and fascinating shadow across our understanding of galactic history. While we often assume that satellite galaxies like Leo I formed alongside the Milky Way, born together from the same primordial matter during the early stages of the universe, its strange properties and trajectory beg a deeper question. Could Leo I be an outsider? A cosmic interloper that wasn't born within the Milky Way's gravitational sphere but was instead captured from another system, or even formed far beyond our local domain. To unpack this, we must start with the notion of galactic accretion, the cosmic process through which larger galaxies grow by consuming smaller ones. The Milky Way is no stranger to this. Stellar streams such as those from the Sagittarius dwarf galaxy or the Helmy stream are remnants of such devoured satellites, long since stripped of stars and momentum. If Leo I were native to the Milky Way, it might be expected to show a history aligned with the rest of the galactic family, a similar orbital structure, consistent velocity dispersion, or patterns of chemical evolution familiar in other bound dwarfs. But instead, Leo I bucks many of those trends. First, there's its high velocity, nearly 200 kilometers per second relative to the Milky Way's center. This is exceptionally fast for a satellite galaxy. In fact, if this velocity proves sufficient to escape the galaxy's gravitational hold entirely, it suggests Leo I was never deeply bound in the first place. Most satellites on long-term orbits tend to sink inward over time due to dynamical friction, eventually being torn apart. But Leo I seems to be on a flyby trajectory, possibly on its first close approach. That behavior doesn't align with a galaxy that's spent billions of years orbiting a host. Instead, it aligns with something else, a recent arrival from farther afield. But if Leo I was captured, where did it come from? One possibility is that Leo I is a former member of a smaller galaxy group that merged with the Milky Way. Galaxies often move in associations, bound not to a single galaxy but to a shared dark matter halo. When one member of the group falls into a larger system like the Milky Way, its companions can be pulled along, each on a slightly different trajectory. These group infalls are predicted in many cosmological simulations, and Leo I could be a leftover from such an event. Perhaps it once orbited a larger dwarf galaxy, now destroyed or merged, before being tossed into the Milky Way's domain. In that case, Leo I may be the last surviving trace of a cosmic clan now scattered or absorbed. Alternatively, Leo I may be not captured, but captured momentarily, a visitor from beyond the local group itself. It's conceivable, though rare, that small galaxies formed in relative isolation, away from the influence of massive galaxies. These loners can drift for billions of years through the cosmic web before their paths bring them near a gravitational giant like the Milky Way. If Leo I is one such case, its trajectory could represent a transient arc, not a permanent orbit, but a brief gravitational flirtation. Such a flyby would be nearly unprecedented, but not impossible. Simulations of large-scale cosmic structure occasionally reveal dwarfs on loosely bound or even hyperbolic paths. Supporting the outsider theory are a few key observational quirks. Leo I's stellar population is notably old, but it also has a small subset of unexpectedly younger stars, suggesting that interactions may have sparked late-stage star formation. These bursts could have occurred during a gravitational encounter, hinting at a recent passage through a more dense or active region of space. That could include a previous brush with another galaxy, or with a large-scale structure like a dark matter filament. These regions can compress gas, igniting a flurry of star birth before the galaxy moves on. Another compelling clue lies in its metallicity, the abundance of elements heavier than helium within its stars. Leo I's stars show a relatively wide metallicity spread, with some being extremely metal-poor, and others surprisingly enriched. This suggests a complex formation history, with multiple epochs of star formation and chemical recycling. Such complexity could arise in an isolated galaxy, or in one that underwent intermittent tidal interactions with multiple systems over time, before falling into the Milky Way's vicinity. Either way, it hints at a chaotic past, more convoluted than a quiet life as a loyal satellite. One also has to consider the possibility that Leo I may have been drawn in by a secondary agent, another satellite galaxy acting as a gravitational shepherd. The Large Magellanic Cloud, for instance, is massive enough to tug on smaller dwarfs and may have once had its own retinue. Perhaps Leo I was formerly bound to the LMC, caught in its orbit as the Magellanic Clouds began their journey toward the Milky Way. In that case, Leo I would be a second-order capture, not grabbed directly by the Milky Way, but carried in by another infalling galaxy. This theory is particularly intriguing given the LMC's large mass and its significant effect on the Milky Way's dark matter halo. The LMC is suspected of dragging its own dark matter wake, and it's possible that this gravitational feature could have altered Leo I's trajectory. If Leo I passed through this wake, or near the LMC itself, its velocity may have been boosted, a kind of gravitational assist that helped sling it outward. In this scenario, Leo I was native neither to the Milky Way nor to deep intergalactic space, but rather to another satellite system entirely, making it a cosmic hitchhiker. Yet another possibility is that Leo I is the remnant core of a much larger system. Over time, the outer layers of galaxies can be stripped away by tidal forces, leaving behind a dense nucleus. These stripped remnants can be hard to classify. They may look like dwarf galaxies, but carry the kinematic memory of larger systems. If Leo I was once embedded in a more massive structure, possibly a progenitor of several current dwarfs, its path and properties could be the final echoes of that long-vanished ancestor. And finally, one must entertain the idea, remote, but not absurd, that Leo the First is not a native structure at all, but something older and more exotic. Could it be the remnant of a primordial dark matter halo, formed in the early universe and only now lit faintly by a few bursts of star formation? Could it even be a survivor of the first galaxies, drifting for billions of years until it brushed past our galactic neighborhood? These are questions that can't be answered yet, but they remind us just how little we still know about the earliest epochs of structure formation. Leo I's true origin remains unsolved. But each of these theories, captured dwarf, intergalactic loner, group remnant, LMC companion, stripped core, or ancient relic, adds a dimension to our understanding of what galaxies are and how they move. What's certain is that Leo the First challenges the neat categories astronomers once used to define satellite galaxies. It shows us that galactic history is written in orbits, in stars, and in motion, not in position alone. And as we trace Leo I's past, we don't just uncover its story, we uncover the story of the Milky Way, and of the cosmic currents that carry galaxies through time and space. Now that Leo the First appears to be racing away from the Milky Way, our gaze turns toward the road ahead, not just where it's going, but what it may become. The future of Leo the First is as uncertain as its origin, yet it's filled with intriguing possibilities. This small, dim galaxy, seemingly insignificant compared to the giants of the cosmos, is writing a rare kind of destiny, one that may unfold far from any galactic host, deep in the uncharted wilderness of intergalactic space. If Leo I's velocity continues to exceed the Milky Way's escape speed, then gravitationally speaking, it is already free. It will no longer return in orbit, and the tug of the Milky Way's gravity will grow weaker with every passing million years. That means Leo the First will transition from a bound satellite to a truly independent galaxy, unanchored from any massive neighbor. For a dwarf galaxy, this is a perilous but fascinating fate. Out in the void, Leo the First will become one of the universe's few known examples of an intergalactic dwarf, a solitary traveler cut loose from the bustling cities of galaxies and star clusters, wandering in the cosmic desert. Its motion suggests that it may not remain within the local group forever. If its trajectory continues outward at its current speed, around 200 kilometers per second, it may eventually cross the faint, gravitational boundary that defines the local group itself. Beyond that lies intergroup space, where gravitational influences from the Milky Way, Andromeda, and Triangulum fall away, and a galaxy becomes truly alone. This is a realm sparsely populated, where galaxies are fewer and farther between, and where interactions become increasingly rare. There, Leo the First will no longer be shaped by tidal forces or encounters with other galaxies. It will be governed only by its own gravity, its own dark matter halo, and the slow, aging heartbeat of its remaining stars. But this raises a haunting question: can Leo the First survive on its own? The odds are difficult to predict. On one hand, Leo the First appears to have a reasonably intact dark matter halo, which is crucial for its long-term structural stability. This halo acts as a kind of gravitational shield, preventing the galaxy's stars from dispersing too easily. It also means Leo the First has the internal cohesion necessary to persist as a unified object, even in the vast emptiness beyond galactic clusters. In this regard, Leo the First may continue to exist for billions of years, its stars slowly aging, cooling, and dying, but remaining gravitationally bound in a cosmic ember that drifts between galaxies. However, Leo I's internal dynamics suggest it's already weakly bound. It's diffuse, low in mass, and composed mostly of ancient stars with only a sparse population of younger ones. There's little to no star formation happening today, and its reservoir of gas, if it ever had much to begin with, is likely depleted or stripped away during previous encounters. That makes Leo the First a quiescent galaxy, one that's coasting on momentum and memory rather than active creation. If it's truly severed from all major gravitational influences, and without any inflow of fresh gas from a galactic environment, it will likely fade further, becoming ever more ghost-like over time. One risk, though small, is evaporation, not in a thermal sense, but gravitationally. Over very long timescales, especially in isolated systems with low mass, the motions of individual stars can gradually lead to the dispersal of the galaxy's structure. This is especially true if Leo I's dark matter halo is less massive or less stable than current models suggest. Over billions of years, without reinforcement from mergers or new material, Leo the First could slowly come apart, becoming a stream of stars drifting across the dark. If this happens, it would leave behind no luminous core, only a subtle streak in the cosmos detectable perhaps only through deep surveys and sensitive instruments. Yet, the opposite is also possible. In its isolation, Leo the First may find stability. Without external tidal forces stretching or shredding it, and if its dark matter is sufficient to hold it together, Leo the First could become a fossil galaxy, an ancient, stable system coasting quietly through the void. Such galaxies are incredibly valuable to astronomers. Untouched by modern galactic interactions, they act as time capsules, preserving the conditions of the early universe. Leo the First may one day be the perfect target for a future telescope mission, an example of galactic life that never merged, never collided, never changed, except under the gentle force of its own mass and time. Interestingly, its trajectory may not be a perfect escape into infinite solitude. The gravitational web of the cosmos is vast, and while Leo the First may escape the Milky Way, it could still become entangled in a new gravitational environment in the very distant future. If it passes close to another massive galaxy, perhaps within the outskirts of Andromeda's halo, or even another member of a nearby galaxy group, its motion could be altered again. It might become captured once more, re-entering a galactic ecosystem after millions or billions of years alone. These scenarios, while improbable in the short term, are not impossible when viewed on cosmological timescales. The other unknown in Leo I's future is what will happen when the Milky Way and Andromeda merge, an event expected to unfold in about 4 billion years. If Leo the First remains within the local group until then, the gravitational realignment caused by the merger could significantly alter its path. Perhaps it will be drawn back into the new, larger galaxy, pulled by the enhanced mass and deeper gravitational well. Or perhaps the merger will fling Leo the First outward with even greater velocity, using the chaos as a final boost to freedom. Either way, its fate is connected to the grander cosmic ballet playing out in the local group. Regardless of whether it survives as a coherent structure or slowly dissolves, Leo the First's future will almost certainly be lonely. It will travel through a cosmic darkness, illuminated only by the faint glimmers of its ancient stars, too faint to be seen by most telescopes. Occasionally it may pass near a rogue star or a wandering planet, but these encounters will be rare and fleeting. For most of its existence, Leo the First will drift unseen, its story written in trajectories and gravitational echoes rather than in light. Yet, this lonely path is also a profound one. Leo the First will become something very few galaxies ever are, a true intergalactic citizen. In a universe where most galaxies are clustered, interacting, merging, and cannibalizing each other, Leo the First stands apart, a rebel, a pioneer, a traveler not defined by its attachments, but by its freedom. It is both fragile and defiant, a small cluster of stars daring to leave the cosmic nest and venture into the unknown. And perhaps, billions of years from now, another civilization in a distant galaxy will detect a faint, diffuse glow moving quietly across their night sky, a ghost galaxy from another time, another place. They might wonder what it is, where it came from, and how it came to be drifting alone through the silence. And in that moment, Leo the First will continue its legacy, not just a galaxy on the run, but a messenger of the Milky Way's ancient past, carrying echoes of our cosmic neighborhood into the most distant reaches of space. And so, as we step back and watch Leo the First fade into the darkness, we come to the end of this extraordinary tale, not one written in words or spoken in time, but in gravity, light, and silence. In the great story of the cosmos, where galaxies dance and collide, merge and evolve, Leo the First is not one of the brightest players. It doesn't blaze across the heavens like Andromeda or sprawl with the grandeur of the Milky Way. It is not vast, not powerful, not even easily visible to our naked eyes. But that is precisely what makes it so moving. Here is a galaxy so faint it took decades of effort just to detect it, its stars scattered thinly across space, its light barely whispering across the void. A ghost of a galaxy. A shadow, flitting just at the edge of vision. And yet this wisp of matter is moving with defiance, with speed, with momentum that shakes the very foundations of how we think galaxies should behave. Leo the First is tearing itself away from its parent. Whether it was born here, captured, or only ever a visitor, no longer matters. Its motion is its message. It is saying no to gravity, to confinement, to the ancient bonds that hold most galaxies in place. It is breaking the rules written in the sky since time began. We watch as it moves, relentless, deliberate, almost poetic. Stars older than any civilization drift at its heart. Supernovae echo from long ago. It has felt the touch of the Milky Way's tidal pull and chosen not to stay. It may once have circled close, brushed past the core, exchanged gravitational glances with dark matter and starlight alike. But now it pulls away free. What Leo the First does is rare, perhaps even unprecedented in our corner of the universe. Most satellite galaxies remain loyal captives to their masters, locked in orbits that spiral inward. Some are devoured. Others are shredded into stellar streams. But Leo the First? Leo the First flees. It races past escape velocity. It dares to drift beyond the Milky Way's dominion. It carves a new path not in orbit, but in exile. And in doing so, it challenges our understanding of what a galaxy is, where a galaxy belongs, and how galaxies die, or live. We may never see it again. Its light will dim with distance, its stars will age, its presence will become a statistical ghost in our models of the local group. But it will still be there. In the cold, dark places between galaxies, where the background radiation hums quietly, Leo the First will press onward. A runaway satellite. A fugitive. A whisper. Perhaps that is the lesson it offers us, not in numbers, not in mass or velocity or chemical composition, but in metaphor. That even the smallest structures can escape giants. That even something faint can leave a mark. That momentum, once gathered, can carry you beyond the boundaries thought to define you. That destiny, even in the deepest reaches of space, is not something given, but something chosen. Leo the First writes its story now not as a satellite, but as a sovereign. Alone, but not lost. Faint, but not forgotten. A tiny galaxy, barely seen, carving its own legacy in the cosmic dark. The stars at its heart continue to burn, cold and ancient and wise, pulling forward a halo of memory into a future unclaimed. And as we peer after it with telescopes, models, and dreams, we are reminded that sometimes, the most powerful journeys begin with a quiet departure. Sometimes, the most beautiful stories come not from brilliance, but from the persistence of motion, the will to go farther than anyone thought possible. Leo the First, the runaway satellite. A flicker against the black. A question hurled into space. A galaxy not falling, but rising. And in the silence of intergalactic night, it moves. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.